So,
Yeah.
Dattaji, am I supposed to start or you are
No,
going
no,
to
no, sir.
introduce?
I will be doing the morning opening remark with the
Okay.
introduction round, and then I will hand over to you. So, good morning, all the participants and respected speaker, Dr. Ajit Kelkar, sir, in the day 2 morning session of EICT Atal Faculty Development Program on Nanotechnology Advances in Engineering Material and Manufacturing. So I welcome all the participants from the different part of the country who have joined for this session, and we have the renowned speaker for this morning. So I welcome you to this faculty development program at BJTI on the behalf of EICT Atal uh, FDP program. So we have a speaker with us, Dr. Ajit Kelkar. So it is my duty to introduce the speaker for this gathering in the morning session. So many of you might have been interacted and came contact with Dr. Ajit Kelkar, sir. He is a renowned speaker and might have been interacted in many conferences or maybe in another short-term training programs or maybe keynote addresses. So Dr. Kelkar, sir, he did his PhD and MS from the United States, MS from South Dakota State University, PhD in 2000, sorry, in 1981, and PhD from old Dominion University, Norfolk, Virginia, 1985, and his BS from Pune University College of Engineering in 1975. So currently he is a professor in mechanical engineering from January 2021 onwards. So prior to that, he was a founding chairman for the nano engineering department of Joint School of Nanoscience and Nano Engineering at North Carolina A&T State University. He was also a interim director for Center of Excellence in Manufacturing in February 2019 to July 2019. He was also a professor and founding chairman for the Computational Science and Engineering Department of E&T College of Engineering, E&T State University, USA from 2005 to 2010. Uh, Prior to the computational department, he was a professor and he is now continued as a professor in the same department after completion of tenure from the JSNN as a founding chairman and professor of nano engineering department. He had been a postdoctoral fellow in the NASA Langley Research Center during 1981 to 1985. He has industrial experience initially before going for the MS and PhD from Telco, Cummins. These are the two industries. Dr. Kelkar is having more than 25 different companies and the experience as a consultant like aerospace, automobile industries, and then academic institution in the area of structural design and analysis, material and structural failures. So now he is back to the mechanical department and serving to the department. So last 25 years he is working in the same field, but he served to the nanoscience and nano engineering with nanoelectronics, nanomaterial for aerospace, automobile application, nano devices, nanobio. In addition, he also has been working in the area of performance evaluation and modeling of the polymeric composite, metal matrix composite, ceramics matrix composite. He has worked with the several federal laboratories, including U.S. Army, U.S. Air Force, NASA Langley Research Center, National Science Foundation, Office of Naval Research, FAA, Oak Ridge National Laboratory in the area of testing, characterization, modeling of advanced structural material. His experience includes the nano engineering material and low-cost fabrication of processing of woven composite using water methods, fatigue and impact testing of composite. And presently, he is involved in the development of nano-engineered functional material using CNT, BNTT, electron nanofiber material, nano-engineered radiation shield material, and he has secured over over US $35 million of research funding, being a principal investigator and co-principal investigator during his tenure. So he has supervised more than 25 PhD student, 50 MS student under his supervision, and they are mainly working in the different industries in US like IBM, Boeing, Intel, Lockheed Martin, US Army, NASA, SpaceX, Ford, GM, Volvo, Navy, US Air Force, Tata Motors, Tata Consultancy, General Electrical, VJTI, Bharti Debit. These are some of the students who are working, has been noted. Dr. Kelkar has been instrumental in organizing the several research workshops in India for Society of Automobile Engineers in the area of nano-engineered material for aerospace and automobile application. He has delivered over 50 keynote address in the prestigious international conferences at India, China, France, Brazil, Germany, Japan, Australia, Switzerland, United Kingdom, Ukraine, Singapore, Malaysia, and so on. In the area of lightweight composite material and nano-engineered material. Dr. Kelkar has published over 300 papers in these areas. In addition to he has added 2 books in the area of nanoscience and nanoengineered, and he has 3 US patent, 3 patent applications are additional 3 patent are application are pending. 16 invention disclosure in the area of composite manufacturing. He has received numerous awards, including Senior Researcher Award, Intellectual Property Award at North Carolina State University twice, Interdisciplinary Team Research Award, uh, nominated twice for the Max Gardner Award, most prestigious research award at University of North Carolina System, BEA System Education Award, selected uh, for Government of India Global Initiative of Academic Network 2019, and been selected for the Government of India's Prime Minister Modi program, Vaishvik Bharatiya Vigyan Summit as organizer for the Aerospace and Nanomaterial in 2020. He is a fellow of Maharashtra Academy of Science, India. He is currently serving on a editorial board for 3 journals in the nanotechnology areas, and review over 15 technical journals and annual international conferences like ASME, AI, AA, SAMPI, etc. He is a member of several professional societies, including ASME, SAMPI, AIA, ASM, MRS, and ASE. So he has over 300 reference journal conferences, and with Google citation more than 2300 in his record as on date. So we have such a eminent personality and a big, big experience, rich in experience in nano, bio, technology and advances. And he has developed many infrastructure and state of art in the United States. One of the 6 schools developed under his leadership in the North Carolina A&T State University as a JSNN Joint School of Nanoscience and Nanoengineering. So with this few word of introduction, sir, I wholeheartedly welcome to this FDP program, taking your special time. It is a late night in the United States, but you have agreed to deliver the talk. So I thank you so much for your consent and being with us for this early morning at Indian timing. So with these few words, now I request Dr. Kelkar sir to kindly take over the session and continue the session. Thank you so much, sir, for being with us.
Thank you, Dr. Dattaji. Thank you very much. And I would like to welcome all the participants. I'm so glad that you are able to join. I know due to COVID, we cannot meet in person, but this is the Zoom opportunity. We can share our thoughts, and I'm going to give you a little bit glimpse of nano-engineered materials for both aerospace and automotive applications. Depending upon my time, let's see how much I cover. I have a lot of material to cover, but we will see how it goes. So As Dattaji mentioned, I am located in United States, eastern part of United States. The state is North Carolina, as you can see there. And our school is located near downtown. On the right-hand side, you see the picture of Joint School of Nanoscience and Nanoengineering. Dr. Dattaji received his doctorate degree from JSNN, and he was one of the very bright students here with a 4 out of 4 GPA. Uh, so let's get started with, when you look at automotive materials, basically what you are looking, the higher fuel efficiency, they should be lightweight. And that goes hand in hand. When your automobile is lightweight, automatically you will save a lot of fuel, because you can have increased load carrying capacity and increased mileage or increased range, and then low noise and comfort. Also, you have to follow the environmental regulations, like you need pollution standards. In US, for example, they are very strict about pollution standard, and in India, they are adopting some of the California standards. The second last thing is the affordability. You don't want your automotive made out of exotic material, then it can be very expensive. So we want it to be lightweight, but at the same time, low cost. So low cost manufacturing is also key thing. And in future smart materials, as you can see, with lot of sensor development, all the automobiles are getting smart, and that requires basically the sensing applications and how that can be achieved using nanotechnology. I will talk some of those issues. When you look at the aerospace materials, very similar to automotive, but slightly different requirement. In aerospace, you are looking for, main thing is very lightweight, and they have to have very high strength and stiffness. One of the challenges in aerospace is impact resistance, because there are a lot of bird impact or foreign debris impact. The another problem most of the aircraft faces is fatigue phenomenon, and that's why you have to have longer fatigue life. And as I said, the lightweight is very important. And some of the space application requires radiation shielding materials, so that the radiation will not bother the instrumentation of the aircraft as well as the passengers. And the last thing is the future smart materials. So we will try to cover that. So what are the traditional materials people have been using? People have been using for the automotive steel, then aircrafts were made out of aluminum. Magnesium was also considered for lightweight. And recently in last 15 years, the composites have become very popular, whether they are fiberglass for automobile or carbon composites for aircraft. What are the challenges? The steel is strong, but it's very heavy and it corrodes. Aluminum is not suitable for high temperature application, and it's expensive also. The magnesium is also not suitable for high temperature application, and the composites are very strong steel, but one of the challenges is high cost, and they are difficult to manufacture. And also recycling can be the problem. And as I mentioned, they have delamination problem. We'll talk about it, and the poor impact resistance. Why I'm bringing all these things? Because we are going to see how the nanotechnology can help to alleviate some of these problems in the future. So what is nanotechnology? Everybody is quite familiar, but I'm just going to reiterate this. Basically, nanotechnology is, if you look at carefully, it's not only related to engineering, but now it overlaps with the fields of chemistry, biology, physics. Anytime, everything what you study between 1 to 100 nanometers, that's what we call it nanoscale. People loosely use material nanotechnology even for 500 nanometer to 1000 nanometer. But in true sense, when materials are about 1 nanometer to 100 nanometer and their application, then we can say that it's a nanotechnology. As you can see that the estimated growth of nanotechnology, there will be about 2 million workers will be needed. So some of the universities in India have started offering the programs in nanotechnology. In US, several universities now offer MS and PhD degrees so as undergraduate degrees in nanotechnology. So it's very upcoming field and very important field. If you look at this chart from 2000, it was just $40 billion market, and it has grown now this year to more than 3 trillion, which is 3,000 billion dollars of market. And that just happened in 20 years. So it's growing at very, very fast rate. And what it started as a passive nanostructure, now it has been applicable to a very active and nanosystem design. So from rudimentary knowledge of nanotechnology to all the way now, it has been used for very complex applications. So when we talk about word nano, where it originates from, basically it's a Greek word called dwarf. And when we say nano, that is 10 to the power minus 9 as a factor. So when I say nanometer, that is 10 to the power minus 9 meter. So you imagine that just 1 inch will have 25,400,000 nanometers. So you can imagine how nano scale is compared to our day-to-day life. For example, the newspaper is about 100,000 nanometer thick. And if I take a marble and if I compare to Earth, then that's the comparison from 1 nanometer to the diameter of the Earth. The human hair is approximately 80,000 to 100,000 nanometer. So if you look at the scale wise, your DNA is about 2.5 nanometer. And if you go 1,000 times of DNA, you get to bacterial level, which you can see under microscope, which is about 2.5 micrometers long. And if you go another 1,000 scale, then you will get the almost large raindrop. Similarly, if you look at single watt carbon nanotube, we will look at that little later. And if you go 100,000 times, or in Indian language, 1 lakh times, then you get into the strand of hair, and another 100,000 time magnification is about size of house, which is about 10 meters wide. And if you look at nanoparticle, now you're scaling it up by 1 million, it goes to the ant, and another 1 million, that will be about big stadium. So that's how the scale of nano reflects from DNA to single wall carbon nanotube to nanoparticle. So essentially, this nanotechnology was there even in year 1900, something called colloidal science. And what is colloidal? If you look at your milk, milk is an emulsion where there are suspended particles. So that's basically colloidal, say, is nothing but that solution which has 5 to 200 nanometer suspension or emulsion particle. That's what we call nano colloidal solution. So that's how it always existed. And the dispersions of this particle in colloidal is very critical. That means they should remain suspended. They should not settle. Then only we can call it as a colloidal solution. So nanotechnology existed long time back. But really, if you look at this history of nanotechnology, 1959 was one of the key year when Richard Feynman gave a famous talk that there is a plenty of room at the bottom. That's where really it started. And then in 1974, Norio Taguchi, basically he coined the word called nanotechnology. So then in 1985, the buckyballs by Harry Kroto and Richard Smalley, they won the Nobel Prize for the invention of buckyball. We will take a look at what buckyball is and what are their applications. And then in 1991, Sujio Ijima, he basically invented the carbon nanotubes. So now this is very interesting chart. Look at it carefully and look at the year. I'm showing you the chart of strength versus density. This is 3,000 years back, what materials were available. If you look at what materials we had at the first King Menes, there were only natural materials, and that was basically wood, ceramic, and glasses. Ceramic came from basically all these bones, antlers, shells, pottery, and metal was only gold was there. See, this is back in year 3000 BC. And if you look at the chart of strength versus density, there is one noticeable thing that as the strength is slightly going up and up towards metal, the density is also increasing. As time went by, now you can see Julius Caesar time, which is 50 BC. What you can see here is important, just apart from gold, so many different metals were developed, like lead, tin, wrought iron, bronze. So all this material started coming up. In addition to that, some of the ceramic glasses in that concrete got added. But now still one thing you have to notice, that as the strength is going up, the density is also going up. As the time went by, now we are in 1500 AD, that is King Henry the Eighth. Now what you can see is some additional materials, not really too many, but some of the additional few material like tin and other things started coming up, wrought iron started coming up, but not much development occurred during that time. But then roughly in 1837 to 1901, you can see one of the key new material got added is polymers and rubbers. So those started getting in. And as the time went by, during the World War II, you can see several different alloys came, epoxy and polymer elastomers came, and all these different materials emerged. And then in the recent era, look at this material chart, how many new materials have been developed. You can see all the way ceramics to nickel alloys to titanium alloys, aluminum oxide. You can see here polymer and elastomer composites. But one interesting thing you have to note is all the material development has occurred diagonally. That means if you look at the metals, they have very high density, but at the same time, they are very high strength. But in real life, what we want is not high density, but we want high strength. So if you look at the next chart here, this is Young's modulus versus density chart. Again, it's along the diagonal. And if you look at, there is two holes where no material has been developed, and there is another hole there is no material has been developed. But we are not interested in hole which is at the bottom, because what we are interested is something which has a lower density and higher modulus and higher strength. So we are interested in the interesting hole which is on the top. Why? Because the density on the bottom x-axis, if you see, is very low, between 0.01 to 0.1 milli mg per m cube, versus the modulus of elasticity is very high. So can we develop these new materials in this area? And that's how the whole idea of nanotechnology started. And this was not only limited to the strength, but this was also limited to the thermal expansion and thermal conductivity. So as you can see here, there is another hole where you want higher thermal conductivity, but lower or almost no thermal coefficient of expansion. And that hole is there, and that's what we are trying to fill. So what is the next step is develop that those gaps or those holes by developing something called the nanomaterials. So hybridization of this nanomaterial with the conventional material will fill that space, and that's where we are going. So what are different nanomaterials we can think of? So nanomaterials basically fall into, as I said, in nanometer scale, and they can be classified as nanoparticles, nanorods, nanowires, nanofibers, nanofilms, and then the bulk material that are made out of nanoscale building blocks, which makes the nanostructure. So in this classification, if you look at carbon-based nanomaterials, you will see carbon nanotubes, fullerene, graphene. The metal-based nanomaterial, which are very popular, are nano silver, nano gold, quantum dots. And then there are a lot of metal and non-metal oxides which are used in several automotive industries for paint purposes and many other applications. So we'll look at some of the applications and how they are made. So moving forward, the classification of this nanomaterial, we can classify into zero-dimensional material, then one-dimensional nanomaterial, and two-dimensional nanomaterial. and the last one is three-dimensional nanomaterial. So what are zero-dimensional nanomaterials? Basically, zero-dimensional nanomaterials, all the dimensions are measured within the nanoscales, and no dimensions are larger than 100 nanometers. That means all your nanoparticles we can classify into zero-dimension nanomaterial. The 1D nanomaterials are typically nanotubes, nanorods, nanomaterial, because one of the dimension is outside nanoscale. So if you look at the nanotube or nanorod, the length of the nanorod is much larger than 100 nanometers. The two-dimensional nanomaterials, basically two of the dimensions are outside nano range. So what happens is, if you look at the nanofilms or nano layers or nano coatings or graphene layer, the two dimensions are greater than the 100 nanometers. So that's why they fall under two-dimensional nanometers. And 3D nanomaterials are just building blocks of all these 1D, 2D, and 3D nanomaterials. So the first popular nanomaterials, first I'm going to explain what are different material, and then we will look at the applications. So fullerene is the most popular one because it's a molecule of carbon. And from fullerene, basically, the term the buckyball came, and the cylindrical fullerene basically gave rise to something called carbon nanotubes. So we'll look at that. And all these are fabricated using laser vapor deposition, or several other synthetic methods are there making out of helium gas or CVD process. And that's how the fullerenes are made. The structure of the fullerene is very interesting, and that's how the Harry Kroto and Richard Smalley, they discovered this C60, what we call the Buckminster fullerene. That's a name for that, and that's how it emerged as a buckyball, and it consists of 20 hexagons and 12 pentagon carbon molecules, and it can be used for tribological lubricants in aerospace applications. The CNTs, carbon nanotubes, basically they are again allotrope of carbon, and they come in different diameter, different lengths, different functional groups, and they can be classified as single-wall carbon nanotubes or multi-wall carbon nanotube with tremendous applications. They are chemically bonded with sp2 bonds, and they form basically very strong molecular interaction. They have very high strength, lightweight, and exhibit excellent both electrical and thermal properties. There are several, if you go deep into the study of just nanotubes, they are basically classified into metallic or electric nanotubes, and how it is determined is something called chirality. In the graphene sheet, basically you draw a vector, and from that, the value of the vector, you can determine whether the given carbon nanotube is a semi-conducting or metallic. And depending upon that, you can have different applications of these carbon nanotubes. We will later on see some of the applications of CNT for aerospace and automotive application. The nanowires, basically, as I said, 1D structures and a lot of application in electronics, particularly they are made out of silicon, gallium nitride, and indium phosphide. And they have very good optical and electronic properties, and they are fabricated using either CVD or MBE. The next one is later on in the session, I think on Friday, you will have a talk from one of my faculty member, Dr. Zhang. He will spend a lot of time talking about the advances in creating these nanofibers. So you will be able to see how these nanofibers are made at a commercial level and what are the applications. The next one is called quantum dots. Quantum dots are very tiny semiconductor particles. It also has a lot of applications currently for the catalyst, spintronic sensors, and also for imaging the cancer tumors. So quantum dots are getting very popular because of various properties like chemical properties, thermal properties, optical properties. So it has different properties, and that can be used for various applications. So one of the properties of the nanoparticle, if you look at the gold, depending upon the size of the nanoparticle, you can see the wavelength changes, the way in which it absorbs, and it gives the illusion of different colors, not the way in which we see our gold in every day, which is yellow color. You can have gold in red color or violet color or green color, depending upon the size of the gold nanoparticle. One of the other interesting property of the nanomaterial is, as the size decreases, the melting point of for example, here the melting point of the gold uh, can decrease dramatically. And you can take advantage of this to do the printed circuit board like this. In the olden days, it was impossible to print metallic or gold circuits on a plastic film, because plastic will melt and you cannot have flexible displays. But now you can use your ordinary printer and you can have the metallic PCB circuits printed on a just plastic sheet, as you can see here. Here is a flexible display, for example, for the integrated circuit on a transparent polymeric substrate. So these are the flexible displays which you can fold and just put it in your pocket and use it for any applications. So that's the advances in the nano. Other areas in automotive industry, a lot of people use nano clay, which are nothing but aluminum silicate as a principal component. And then also other components are magnesium, calcium, potassium. They are embedded. So you get this nano clay, which has tetrahedral or octahedral structures for the silicon oxide in different forms. And the last one classification is nanocrystals, where the crystalline particles with at least one dimension is in nanomaterials. And they are used in, for example, LEDs as energy efficient lighting. They are widely used in sensors. So this is just a brief overview about what are different types of nanomaterials. But now we are not going to build something out of nanomaterials alone. So that's why this concept of hybridization comes in picture. So essentially, till date, how the materials were classified. When you look at material, they will either fall as metals, polymers, elastomers, glasses, ceramics. But as the time advanced, as you know, that metals, you started getting different alloys. And then hybrids, people started using, for example, polymer with carbon fiber, polymers with glass fiber, getting sandwich structures. So different application. And now virtually any structural part, whether it's made for automotive or whether it is made for aerospace, it's always a hybrid structure. So what I'm going to talk is, now you learned about little bit about nanomaterial. Now we will see what is the role of some of this nanomaterial in real life applications. So I will talk about basic structural composites and what are the challenges, and then how this nano-engineered materials can help us to improve the certain properties. And then from the space point of view, we will talk about radiation shielding material. And then for the smart vehicles and smart aircrafts, how you can create microvascular section in the structure. And lastly, if time permits, a little bit about automotive applications. So basically, the composite materials, basically, many of you must have been working in the area of composite. Basically, there are two or more macro or nano constituents, and the advantage of that is they have high strength and stiffness, very lightweight, and they have design flexibility, and you can do the net shape manufacturing. That means you don't need to do any welding or bolting, joining. You can create directly the part what is needed. That's why consolidation of the parts occur, and that saves a lot of cost. And the applications are started with aerospace, but now it is moving to automotive industry and home appliances also. So essentially, if you look at very popular material what are used in composites is E-glass, S-glass to make the fiberglass composite. some of the Kevlar for bulletproof vest and other things, and then the carbon fibers, and then aluminum, titanium, and steel I have given just to show you how the strength and stiffness, how the density compares. You can see steel is very, very heavy as compared to the carbon. So this is the comparison of different popular materials what are used. Um, so what composite does, the matrix and the fibers. Fibers are reinforcement. Basically, matrix provides the load transfer, and it is temperature resistance and chemical resistant. And the reinforcement provides tensile properties, stiffness, and impact resistance. How they compare to each other. Here are some of the popular fibers I have shown: aramid fibers, carbon fibers, and then fiberglass. And you can see how the fiberglass is the cheapest and the carbon is the expensive. On the other side, the fiberglass is heaviest, whereas aramid is the lightest and the carbon is in between. The strength wise, carbon is very strong compared to other two. So each material has its own advantage, and depending upon its application, you will choose what you want to use. So how things evolved. Um, I remember when I started working, when I was doing my PhD at NASA in 85, the 747, the big jumbo jets, used to have only 1% use of composite. But as you can see, the latest Dreamliner 787, almost 50% of the weight of the aircraft is made out of carbon composite. And here are some of the compositions. You can see 50% is composite, aluminum is 20%, titanium, steel, and other. So as these composite materials are growing in aircraft and automotive industry, let me go one. They pose a challenge, because this textile composite, what they use in all these applications, they use combination of fiberglass and carbon. So they have mismatch of thermal coefficient of expansion. Also, there is an issue of draping. That means if you have a very complex conforming structure, then if you don't use the right textile composite, what will happen is you will not get the conformity with the complex shape, and there will be gaps. So these gaps eventually can lead to the delamination problems. Also, if you look at all the aircrafts, they undergo fatigue loading. When they're flying, they continuously undergo tension compression loading or tension loading on the wing flap. So when that happens over the long period of time, as you can see, the composite delaminates and then it fails. Also, if you look at, I will give an example of the aircraft floorboard. When you walk on the aircraft floorboard, they are made out of lightweight composite, but they are anchored to the fuselage. And as you can see here, uh, eventually there is a separation of the top layer of floorboard to the anchoring mechanism. And what it does is it creates delamination or separation of the surface. So what we are heading at is another application is composite armored vehicle. Here you can see they are made out of different materials, different layers, phenolic layers, electromagnetic shielding mesh, and then fiberglass composite, and then you have alumina cover. So all this complex structure, when they undergo fatigue, they cause the separation of this layer, which is called delamination. In India, you might have seen a lot of wind turbine blades, and these are all made out of fiberglass composite. And during the big windstorm or over the period of continuous rotation under fatigue, this wind turbine blade eventually fails. And that failure occurs because of delamination. As you can see, the crack is growing, and then eventually the blade has failed. And once one blade fails, all other blade fails. And the culprit behind that is the delamination. And how it occurs, that this delamination basically separates the layers from each other, and eventually crack develops, and they separate out and the structure fails. So what people have been attempting to stop this failure, they were trying to use Z-pinning, they were trying to use 3D views and stitching. But all these methods are very expensive and they don't guarantee, because they, although successful in preventing delamination, they weaken the in-plane strength of the composite. So here comes the nano engineering application. So we saw what is interlaminar property, which separates out the layers. Can we use nano engineered material to solve this interlaminar problem? So we are going to look at myth versus reality. So people think that one can build the structure by atom, the entire structure using nanomaterial. That's just not practical. It's very expensive and you're not going to get anything out of it. However, the idea is that we should just smartly use very small fraction of weight of these nanofibers and use the conventional materials and try to improve, if possible, by magnitude, the performance of the composite. So that's where we are going into a nano-engineered material. So first material we will talk about is electrospun fibers. So electrospun nanofiber and how they can be used for structural application. So what are electrospun fibers? Basically, as I said, Dr. Zhang on Friday will give you very detailed discussion about electrospinning. But basically what it is it utilizes electrical force and basically it creates fibers. And these fibers they can be polymer fibers, carbon fibers, glass nanofibers, and their diameters are essentially between tens to hundreds of nanometer. And electrospinning is the only technique by which you can fabricate continuous scale nanofibers. And how this is achieved, there are three factors which governs the diameter of the fiber. One is called electric force, surface tension, and the viscoelastic force. So I will show you how the glass nanofibers are made in the lab. We have set up a few labs. I think one is in VZTI in Mumbai, in IIT also, and then IIT Madras, and then we have one set up in Bharati Vidyapit, Pune. So you can go and see the electrospinning setup and how the glass fibers are made, and they are made using tetra ethyl orthosilicate. These are the various components. I'm not going to go over the chemical reactions, but you will have it handy if you want to make it in your lab, how to make this, the electrospun glass nanofibers. So this is the lab setup, good enough to do the experimental work. It produces significant amount of electrospun nanofibers. If you are interested in continuous nanofiber, you can use a rotary setup as it is shown here, which will create the electrospun nanofibers. Here are the micrographs, ACM graphs of various electrospun nanofiber. One thing you will notice, our definition of nanofiber is 100 nanometers. These are the electrospun nanofibers, which are ranging between 500 to 700 nanometers. But remember, these are not sintered. Once you sinter them, the diameter drops considerably. Here is the before sintering. On the left hand side, you can see the picture. Then sintered at 600 degrees centigrade, and the last one are sintered at 900 degrees centigrade. So that's how you get the sintered glass nanofibers. Here are the pictures of carbon nanofibers. As you can see, they are also made out of different materials, but typically they are fabricated using polyacrylate, which is called PAN, and polyvinyl alcohol, and then they are sintered to get the carbon nanofiber. We did in the lab the experimental testing of this nanofiber as opposed to the conventional glass fibers, and you can see the conventional e-glass fiber had a strength of about 6 to 7 KSI, whereas the electrospun nanofiber, the strength dramatically increased, whereas there was hardly any change in modulus. So you have same stiffness, but fairly high strength. Similarly, we did the 3-point bend test and we were able to achieve the improvement of about 30% over the conventional glass fiber. And the sintering temperature also played key role on the performance of the glass fibers. So once these nanofibers were made, now the next step was how to prevent them, how to use them to prevent the delamination. So this is a conventional composite manufacturing process. So this is a 20-ply thick laminate, glass laminate. And what we did was, in the next picture, you can see between each of these prepregs, we introduced this tetraethyl orthosilicate nanofibers so that the interlaminar strength can be dramatically increased. So once we did that, we then manufactured the panels with and without nanofiber, and then we cut the short beam strength coupons out of that. And the next figure you will see. This is the 3-point bend test. This is the work done by Dr. Dattaji Shinde for his PhD when he was at our school at JSNN. And then he tested them to look at the 3-point bend strength, and you can see here the load displacement diagram. He also developed the finite element model for these 3-point bend coupons. And then he compared his results with the electrospun nanofibers. I will show you the side-by-side comparison. As you can see on the top, when there were no nanofiber, look at the failure mechanism. At the bottom, look at how the specimen failed, and then look at the energy absorbed for the top specimen where there were no nanofibers versus the energy absorbed with the red curve. As you can see, significant amount of energy was absorbed before the specimen fell. And that's exactly we want, not only improvement in load, but the energy absorbing mechanism. That means you are getting higher toughness when you use the nanofiber. Here are some of the comparison of his finite element analysis of glass fiber versus with the glass fiber with electrospun nanofibers. There was about 30% improvement. The next one we will look at is how the nanofibers improved the impact performance. If you look at the impact, as I said, this impact causes a lot of damage in composites. And the whole idea is we want to improve the impact performance by using the nanofibers. So objective was to develop nanofibers using electrospinning and then embed them between the layers. So we used 10 layers to fabricate impact coupons. And then we used C-scan to look at the damage, and then we did the compression after impact. So this is how the schematic looks like to introduce the nanofibers. Here is the complete system setup, what we call the Wartum setup to make the composite. And we wanted to make sure that the nanofibers, what we included in the mid layers or between the layers were weighted. That means they were not dry. We took micrograph and you can see they were all weighted. And then we did using the low velocity impact, the lot of experiments. And here you can see the failure mechanism of the nano-engineered composites. Here is the impact mechanism. And once we tested them, we used the C-scan, and we wanted to make sure that there was more energy absorbed. And how we know that C-scan should show significantly higher damage areas when the laminate has a electrospun fibers. And you can see that as the drop height increased in impact, the panels which were made out of nanofibers embedded in the mid layer, they showed the significant higher energy absorbed compared to the one which didn't have the electrospinning. That was also evident when we did the test, what is called compression after impact. So if you have more damage area, it should have less compressive strength. This is the Boeing fixture, what was used for compression after impact. And as you can see, there was about 45 to 56% decrease when the nanofibers were used. And that's good news, because we do want, that means it has absorbed a lot more energy during impact rather than catastrophic failure of the component. The second nanomaterial we tried was, we tried alumina nanoparticles. So alumina nanoparticle, what we did was, we again used the fiberglass system and the epoxy resin. This time it was structural fiberglass. And then we use alumina particle, which we purchased from Sasol Incorporated for, this was for 110 nanometers. And then we functionalize them so that they're compatible with epoxy. And then we use them for both resin as well as for the fibers. And here are some of the material system configuration. As you can see, the resin modification was done by using again alumina particle, so as fiber modification by dispersing the interfacial layers with the nanoparticle film. And here is the schematic of the particulate dispersion. You have to sonicate this alumina particle in the resin and then disperse them. And then you have to make the prepregs and make the composites. So here, first time when we didn't functionalize this nanoparticle. So since they were not functionalized, they used to agglomerate. That means they will group with each other. But when we functionalized, they nicely dispersed and we got a lot better results. So here are some of the pictures of functionalization. And then we had 5 different components. We did baseline epoxy H2 glass, resin modified with pristine alumina particles, and then resin modification with functionalized alumina, and then fiber modified with alumina, and then fiber modified with functionalized alumina. So many different combinations. And when we compared the fracture toughness of these values, as you can see here, there was a 74% increase for the last material system, where we used the functionalized nanoparticle with functionalized with the resin as well as for the fibers. So that gave the best mode 1 fracture toughness results. So there is a significant amount of improvement by just adding very small weight percent of nanoparticles. And this is fairly easy to achieve. So next one, we will look at aerospace coatings, how nanotechnology is being used. So aerospace coating, basically all aircraft, one of the biggest challenges is lightning protection and the electromagnetic shielding. These are the two challenges everybody faces. Another is erosion and then de-icing. In the Western countries where there is a lot of snowfall, they have to undergo de-icing. It takes a lot of waste of time on the runway before aircraft can take off. And then corrosion protection. So in erosion, if you look, that occurs because of dust, sand, stone, rain. The lightning strike directly affects the structural performance. It creates significant amount of damage. The ice accretion, again, as I said, de-icing is very important. Otherwise, the aircraft structurally cannot function properly. The corrosion, because of solar radiation or temperature cycling or moisture, salt, atmosphere, or this de-icing liquid, all this causes corrosion. So you need some aircraft coatings, and that's where a lot of nanotechnology is used. They use 3 different type of coatings. Sorry, 2 different types of coating. One is called polymeric matrix nano coatings, and second is ceramic matrix nano coatings. The applications, particularly for polymeric matrix nanocoatings, are electromagnetic shielding, and then structural health monitoring, and then for tribology coating and for structure. As you can see, I will give one example for electromagnetic shielding. They use epoxy carbon nanotubes or epoxy carbon nanotube fibers, and then for the structural health monitoring, typically piezoelectric PVD, F and PGTs are used along with epoxy. And then if you look at for structural application, polyamides, high temperature resins with clay, or epoxy with clay, or epoxy with CNTs are used as a structural material, which are main load carrying component of the aircraft. For the ceramic matrix nanocomposite, main application is alumina particle or CNT particles for the EMF shielding. And for the tribology, they use tungsten carbide or tungsten sulfide or diamond-like coating on the carbon. So these are the various application of coating. This lightning protection and electromagnetic shielding, as I said, directly affects and damages. So what they do is, if you look at here picture, they use the copper mesh, which is a metal foil, they call it. But this copper is very heavy. So people are trying to come up whether nanotechnology can be used instead of this copper mesh or copper foil. So different materials that has been, if you look at the properties of different material, naturally copper here in the graph, if you can see, as far as electrical thermal properties are concerned, copper is the best. But if you look at the density, it's 8,930, very, very heavy. So on one side, you want the best properties. On the other side, you want to have reduced weight. So other alternative has been CNT-based composites. They also have a good performance, and the weight is very low. And then you have combined composite with metallized fibers. So I will come to that little later. And then ICP-based composite. So these are some of the applications. So we will look at how the CNT-based composites are made. We did it in the lab, and I will show you some of the picture. For the erosion purpose, the sand particle, dust, rain, mix ice, they use typically nickel nanoparticles or titanium sheets in pure polyurethane, or blend of polyurethane and polyurethane coatings. So that's how they do to prevent the erosion. Then for icing and de-icing, what they do is they use CNT paper, which can be heated. When you pass the current, it gets hot and it melts the ice. So that's how they embed the transparent multi-wall carbon nanotubes or single-wall carbon nanotubes, and do the CNT paper, or also called bucky paper, and then try to melt the ice. So that's a popular technique. The other one is graphene based coating. So here is the graphene paper, graphene based composite layer. And again, same thing, you pass a current and it will melt ice. So here are some of the pictures of graphene based coating. So we looked at the different aerospace coating. The substrate is composite, and there is a primer, and then the top coat is polyurethane, which will be mixed with a variety of different nanomaterials like carbon nanotubes or any other material. So let's look at the lightning strike protection as first example. So here is that one picture of the actual lightning strike occurring on the composite aircraft. And if you look at the examples of damage, if you look at most of the lightning strike, where it affects is when the aircraft is about 10 to 12,000 feet. That's when it experiences about 20% of the most of the lightning strike. And what it does is the lightning strike causes significant amount of impact damage on the composite, and that causes structural failure. So it's very important to have a coating on the aircraft composite aircraft, which will be lightning protected. So the motivation for us was we wanted to look at whether we can use the carbon nanotubes and that we will disperse in a polymer and see if we can use them for the lightning protection. So we use XT-CNT, which are multifunctional nanotubes. And here is the picture of lightning strike damage. And as I mentioned to you, currently people are using foils, wire mesh, aluminum flame, spray coating. All these are heavy, very heavy. So we were trying to replace this with a carbon nanotube. So if you look at the picture on the right-hand side top, we used just a small amount of carbon nanotubes in polymer, made it electrically conductive. We did some molecular dynamic simulation of interaction of carbon nanotubes with polymer. And then we found out that about 0.15% by weight was adequate to achieve the properties what we needed. So we used XD, CNT single wall nanotubes and multi-wall nanotubes. And what we wanted to do was we wanted to improve the electrical conductivity. So once we bought the nanotubes, we functionalized them so that they can have better interaction with the polymer molecule, which is epoxy EPON 862 molecule. And once we functionalize them, then we manufactured these coupons. As you can see, the right-hand side yellowish color is the pure polymer, and the left-hand side and top are two different concentration of carbon nanotube, 0.15 and 0.015% by weight. If you don't functionalize the right-hand side, you can see the sample, same amount of carbon nanotubes, but since they were not functionalized, they agglomerated. And if you look at the color of the specimen, it has not turned uniform black, whereas the one which is on the left-hand side, you can see they were completely functionalized and they were sonicated and they dispersed very well. That's very important thing. We looked at some of the how these carbon nanotubes affect the mechanical properties. So we looked at the tensile modulus of functionalized and non-functionalized carbon nanotubes, and we found out that there was not a whole lot of a difference in tensile modulus. So as the flexural modulus, they were almost same. But interestingly, we found that the flexural strength was much higher in the case of the carbon nanotubes when they were functionalized and when we used 0.15 weight percent. The next one I'm going to talk is the radiation shielding material. So here is the NASA nanotechnology roadmap, different materials since 2002. It has been implemented, and for a variety of different reasons, weight savings and sensors and radiation shielding, how they are being integrated into the conventional material. So this shows that. So now in our lab, we wanted to address the space radiation, particularly for the long duration of space. I'm going to play one video. My hope is that this video will play what motivated us. One second. I'm playing this video. It's about 2.5 minutes video. And let me know whether it. Dattaji, can you see it?
Space radiation is it's
Yes,
a
sir.
show
We can see it and hear properly.
for future space travel, for long duration travel. I mean, in the past, we've had short missions. If you do longer missions, the radiation dose that the astronaut would receive would be higher. I mean, radiation dose is accumulative. The longer you are there, the more radiation dose you get. And right now, for a long mission to go to Mars and back, we can't do it. So we've got to have better radiation shielding materials in order to do that. I'm looking at this experimentally and computationally. I'm trying to design a better radiation shielding material. The smaller the element, the better it is, the more effective it is for breaking up these larger particles. Now, why do we want to break them up? We can't stop them. So the next best thing we can do is break them up into smaller things that are less damaging and less hazardous. So I'm looking at light elements. In particular, I'm looking at hydrogen and boron and nitrogen because I think that we can get the most bang for the buck, if you will. One material ingredient that we're using, I guess we can call it an ingredient, is the boron nitride nanotubes. Boron nitride nanotubes are composed entirely of boron and nitrogen. Boron absorbs neutrons very effectively, and neutrons are one of the radiation species that we're trying to stop. And so the boron does a very good job of absorbing neutrons. Nitrogen does an okay job. And the two together, do a really good job. The materials we're looking at are not only radiation shielding materials. They're materials that are structural materials that we could also use for building the vehicle, the habitat, the rover, the spacesuit. And then these same materials could be used on Earth, for high altitude aircraft. They have a radiation problem. Pilots on high altitude aircraft, the Concorde, for example, they wore dosimeters. They were classified as radiation workers because they were flying in a radiation environment. It's down here on Earth, there's not, that much, but at high altitude, there is quite a bit of radiation. Not as
Okay, I think I lost. I will restart. But you got the idea about what's going on. Let me open the. Sorry about that. I'm reopening the presentation. Okay, give me 1 minute. Okay, Dattaji.
Yes, sir.
Can you see my screen or not yet?
Not yet shared, sir. Can you share?
Okay. Let me share. Let me go here and share screen. Give me 1 second.
Yeah.
Now?
Yeah, it is shared now. We can see
Now
it.
I will go in the presentation mode again.
Yeah, please go ahead.
Okay. Can you see it now?
Yeah, we can see it.
Okay.
Perfect.
So as you are watching that video, basically the radiation is a key thing for the long space missions because you are talking here 6-month space mission and there are these prolonged radiations which are basically neutron emissions, which are high energy electromagnetic waves, which are very dangerous, and they cause not only harm to human but also for the structural parts of the spacecraft. So basically space radiation, it consists of a variety of different things, which is called solar particle events, the galactic cosmic radiation, and the secondary neutron. I don't want to bore you with the things, but what is important is what we want to do is we want to develop materials which will absorb this radiation, and you cannot use the heavy metals like lead because lead is very heavy and it's just impractical to build the spacecraft out of lead because it will not fly. So we want to come up with efficient material which is lightweight, at the same time will be radiation blocking. So if you look at this picture here, radiation contains alpha, beta, X-ray, which you use, when you go to dentist or anywhere, gamma and neutron. The worst one, what in the space you experience, and you can see this picture, neutron. Not, for example, if you look at the gamma rays, it is blocked by lead, iron, and other thick metal plates. But if you look at neutron, neutron penetrates everything, except the only thing which prevents penetration is water. But you cannot have water blocks or concrete blocks in the aircraft or spacecraft. But then it's very interesting that water, why it prevents, because it has the hydrogen molecule, which is the highest charge to mass ratio, and that's what it stops. So we want to make use of this idea of hydrogen, and that comes from every polymer is a hydrogen rich material. So we wanted to see just plain polymer blocks, how much radiation it prevents, and then enhance these polymers with the nanomaterial. So we looked at the various ways we can stop this radiation, or what we call do the radiation shielding, the neutron radiation shielding. So we tried various different materials along with the polymer and developed these sandwich composites. So when you are looking at that video, you saw that one of the components which is of interest, which has a very high neutron capture cross section, which is boron, and the other material is called galadium. So galadium is gadolinium, is little bit heavy, but both boron and gadolinium are very attractive. When they are embedded in matrix, they can be used to stop the neutron radiation. So what we did was we used boron powder and boron nitride nanotubes, as well as gadolinium nanoparticles along with the resin. And let's look at how they performed when we used that. So the steps involved where we did the fabrication of core material with the nanoparticle, and then we tested them for the radiation shielding, the facility in Pennsylvania, and we looked at how much radiation was blocked. And here are some of the steps of creating fabrication of core panel. Again, we use epoxy resin with W as hardener, and 3 different nanoparticle by 3% by weight. One was boron nanopowder, second was boron carbide, and third was gadolinium nanoparticles. So these particles we used and then prepared our composite along with the sandwich block. So we developed this multifunctional sandwich material using the Waterm technique. I have patent on that. And then this is how the space shuttle tile typically looked like, with the core made out of the polymer embedded with this either boron or boron carbide or gadolinium nanoparticle. And then we subjected all these materials to neutron attenuation testing with a Brazil nuclear reactor. So it does the accelerated neutron testing. And what we observed was that the shielding efficiency without the sandwich panel with the boron, epoxy boron nanopowder was about 72% of the harmful radiation was shielded. But that was not enough. So what we did was we did the sandwich panels, and we were able to achieve as high as 99.6% the radiation shielding. So once we did that, we wanted to make sure the structurally these sandwich panels are stable. So we did the flatwise compressive testing of this panel, and we observed that they performed really well. And actually the radiated one had an improved strength because more cross-linking of the epoxy resin occurred. So this was the, so one of the challenges what we faced was that the gadolinium particles, when they were put in the core material, being heavy, they used to settle down. So what we did was functionally graded shielding structure. That means we built this core layer by layer so that even if they settle, they basically were cured, and then second layer was formed, third layer was formed, and that's how we achieved the next one I'm going to talk is the future smart materials. How to create, when if you are working in composites, they're thin. How you can drill holes or make a channels in this composite. So this is the idea how our body has the nervous system. You can achieve that by creating what we call the microvascular channels throughout this composite. And this idea is very simple. It's basically what it is doing is it does the biomimicking network of channel, because normally the composite thickness is too small to cut or drill after the composite is fabricated. But this biomimicking or making this microvascular section is very important, because this can be used for self-healing structure or structural health monitoring. You can do it for thermal transport. For example, once you have this microvascular channel, your thermal transport application, you can see the cooling will occur like a fins. Some material around the jet engines, where the temperatures are very high, you can create the microvascular section. So here are some of the applications of self-healing. If there is a crack, automatically the resin will seep through and cure and prevent the crack propagation. So structural health monitoring, not only that, it also tells you the location and severity of damage due to fatigue impact once you have this microvascular section. So our objective was how to create this microvascular section and how to characterize them and to model them. So I will show you what we did to create this fabrication of microvascular channels. So people have used glass tubes, metal tubes, wire, many other different things. Our focus was more on evaporating polymer concept to create this fabrication of microvascular channel. So in microvascular channel, what we decided was that we will, while making the composite, we will use something called PLA fibers, which are polyactic acid fibers, and I will show you in the next slide what it is. So these fibers have a melting point of around 300 degrees F. Remember, you cure your composite about 250 degrees F. After that, if you cure, and if there are this biodegradable polymer made out of polyactic acid at 300 degrees F, what happens is they go into gaseous stage and they evaporate. And then those, happens is it leaves the channel, which are called the microvascular channel. If you look at the next picture here, we have embedded this PLA fiber, you can see, and then it was subjected to high temperature, and then after that this PLA fiber disappeared, and it created a very beautiful, nice through the thickness holes, which are microvascular channel. As you can see in the next picture here, I have put copper wires through the thin composites, because that's where the polyactic acid fibers went into the vapor stage, and it created the nice channels. Here is the optical microscope pictures of, on the left hand side, you can see the polyactic fiber through the thickness. On right hand side, it has gone into gaseous stage and it has created a through hole, which you can see with the black dot in the center. Or if you look at the next picture, here you can see the black dot. These are a much closer picture of the same microvascular cell. You can see the composite toes and nice microvascular channel created, and some more close-up picture of this. You can see the beautiful microvascular channel created to those. And here you can see the different fiber toes. So once these channels are created, They act like uh, passages for monitoring the damage or embedding the sensor or whatever you want to use. So all your automotive applications or any other application, you can deploy this simple technique. And you can have the complex fiber structure. Here, for example, currently we are working on this complex PLA fibers to develop uh, different applications for the microvascular channel. Now I will briefly go over some of the automotive applications, nanomaterials for automotive applications. So nanomaterial for automotive application, that this is an emerging field right now. The most popular one right now is the scratch resistant paints, or another popular one which is coming up is in lithium ion batteries, the coolant for the radiator by adding, and then nano adhesives, and then anti-reflective coating, and then nano composite for structural panels. So some of this work is underway. Let's look at what are the different things and what are the different applications. So you can divide these nanomaterials in automotive application into two areas. One is structural and second one is non-structural. And in that you can have timing belt cover, engine cover, interior cover, then coatings, headlamp covers, even tires. Tires uses a lot of nanomaterial, nanotechnology nowadays to improve the tire performance. And then you can have for the body coating. So for example, Toyota has been using the clay, nano clay, which we saw in the first part of the lecture, along with the nylon 6, which is a extrafoliated synthetic clay, 5-atom thick. And that since they have been using in 1993. And so as they were using nanocomposites for bumpers, body panels, fuel tanks, etc. Also, the General Motors, they have been using the thermoplastic with olefin with nanocomposite, basically around the engine area where there is a high temperature. And that's where they were trying to use this addition of 1 nanometer flakes around the thermoplastic resin. So they have been using since all their Safari and Astro model. So every time you do the lightweight 10% reduction in weight, basically it improves 7% in fuel efficiency. But one of the problems of the lightweight composites is the stability and crash resistance. Also, the materials near engine requires very high thermal resistance. So you have to use high temperature nano particles embedded in the conventional epoxy resins, what we call the nano-modified thermoplastics that can help to solve that problem. So lightweight, let's look at here. So broad areas in automotive right now people are using is the nanofluids, and that is for coolant, the tires, the scratch resistant coatings, the mirrors and reflectors, and then little bit for interior. So if you look at automotive nanofluid, the radiator frontal area reduction you can achieve by 18%, and fuel efficiency can be improved by 5%. So how you do that? You can either do as a coolant as well as you can modify the transmission fluid, and for that you can use reduce friction by using copper oxide nanoparticle in transmission oil, or you can use in the coolant again copper nanoparticle. So if you look at the next slide here, here is the nano-modified radiator coolant. The problem is these particles try to agglomerate. So you have to sonicate and functionalize so that they don't group together. Otherwise, it will not solve it will not be useful. The purpose is to disperse these copper particles throughout the coolant. That's why you need to functionalize them. And then you can improve the performance of the engine. So nano-modified coolants, basically it involves base fluid thermal conductivity. Nanoparticle diameters play important role. the volume fraction, how much you should use, and the temperature of dispersion, and then the solid particle thermal conductivity. These are the parameters which characterize. And the next chart shows various. If you look at your current automobile, most likely you are using ethylene glycol as your radiator fluid. But if you mix them, look at the thermal conductivities of ethyl glycol. It's very, very low, less than around 0.2 watt per MK. Whereas if you look at just addition of little bit of copper or aluminum or zinc or nickel or silica or iron nanoparticle or metal oxides, suddenly your thermal conductivity can improve dramatically. So if you look at here, how the thermal conductivity improves by just addition of on the x-axis, if you can see the volume fraction is just addition of about 1.8% volume fraction. The thermal conductivity jumped from 0.22 to almost 1. So that's a 5 times improvement, just adding in conventional your ethylene glycol solution with the copper nanoparticle. So this research is taking off in US, getting more popular to not nano-modify the coolant. As far as tires are concerned, in automotive applications, if you look at the size, basically 1 nanometer to 100 millimeter. So essentially the application, the Bridgestone company or Firestone company, what they are trying is they are modifying the rubber and carbon black compound with silica nanoparticle to improve the tire performance. So this silica nanoparticles, basically they are trying to marry with the rubber molecules to improve the silica dispersion, because that will benefit the better tire performance. And what they observed here is silica nanoparticles in rubber and tire. You can see the higher storage modulus for the nano-modified rubber. The last one, I want to talk a little bit about the scratch resistance coating. So if you look at typical automobile in US, these are the 5, you have the substrate, which is your body of the automobile. On that, there is the electrically applied coat, what they call E-coat. Then there is a primer, then there is a base coat color, and then there is a clear coat on the top. So if you do a car wash, how the wear occurs, or if you abrase it with a keychain or a belt buckle, or if you hit the shopping cart on your automotive, how the damage occurs on the coating. So the whole idea is, if you have a hardening material which is very efficient, either aluminum oxide or zirconia oxide or titanium oxide or silicon oxide, that hard coat basically prevents the scratching, and that improves the surface preparation of the automobile. So they are getting more and more popular. But at the same time, the loading, for example, if you add too much nanoparticles in the coating, you don't want that. They become brittle or too ductile. So you have to optimize and try to get maximum tensile strength. So here it shows the loading of silica particles in the coating nanosilica, and you can see that about C value is about 3.75% by weight gave the best scratch resistant coating. Another area in automotive application is reflectors. When you are driving in the night, if you don't have nice coating on your rear view mirror, you get all this glary, like you can see on the conventional left hand side. But if you have this aluminum oxide transparent coatings, nano coatings, or fluoroorganic layer, then it gives beautiful rear view anti-glare images. So that has becoming very popular. Interior, people are using titanium oxide to prevent dust accumulation and static electricity. And the last one, a lot of research work is going on in the area of catalytic converters. What traditionally they were using were not nanoparticle, but the microparticles, and they used to agglomerate. And then the purpose of, once they agglomerate, they used to become big particle. And then the purpose of catalytic converter was, because when they were heated, it was not uniform. But now with the nanoparticles, now they remain dispersed and you get better pollution prevention. So how the future of the automobile will look like? Here is the nice chart. You can see how the catalyst will change. Ceramics with improved catalytic, reduce emissions, nanofilms for water repelling windshields, distributed solar cells will come, high brightness nano-enhanced polymer displays, sensors for oxygen temperature, magnetic field acceleration, fast change batteries, polymer composite panels for stiffness, carbon nanotubes alloys for lighter frames, nanopowders, because the cost of all these nanomaterials is coming down rapidly, and that's why it's possible to use all these materials. Last one more slide, how the future Ford companies, the latest vehicle looks like. They are targeting 1 liter 3-cylinder engine with a windshield glass, hybrid chemically toughened laminate, 35% lighter than the regular glass. Instrument panel also made out of carbon fiber. Rear window made out of polycarbonate, again instead of glass. Suspensions made out 50% lighter, carbon black and carbon nanotube. Brakes are sprayed with the coating, and the seats are made out of carbon fiber with 17% weight saving. So that's how they're targeting the. So here I'm going to conclude my talk. I would like to acknowledge so many different sources and literature. And just last cartoon slide. If nothing works, then you can use always carbon nanotubes or drink Coke. So I thank you for your attention, and Dattaji, I will hand it over to you.
Yeah, thank you, sir. Thank you so much for this, wonderful presentation and covering all the aspect of nanomaterial, current status, current state of the art of manufacturing and developing the nano-engineered material using the engineering technology and their prospective application and state of the status of the current applications in the industries, aerospace, automobile industry and other industry. It is a very good presentation at one place, covering the aspect, properties as well as the future prospect, looking ahead for this kind of material. So now I will take few of those questions from the participants, and then finally we will conclude the session. So I request the participant, you can ping your question in the chat box, or you can ask your question by unmuting yourself. So our speaker is ready to take your questions. So over to you, all the participants, those who are interested, voluntarily come forward.
Good morning, sir.
Yes.
Sir, this nanotechnology is not utilized in automobile. It is not utilizing for any safety purpose, like in the bags, like airbags or anything, because we have lots of applications.
I'm as far as I'm not aware that they are utilizing yet in the airbags. At least I'm not. We have company here called Takata. They make this airbags, but I don't think I talked with them. Maybe their lab they might be experimentally trying, but I don't think they have yet applied it directly to the auto. It might be still in research stage right now. So only really application, if you look at automotive, real life application is only in the tires and coatings, and recently in the radiator cooling, modifying the ethylene glycol with the copper particles. So that has been adopted, and definitely on the reflective rear view mirrors, you get them everywhere, the coatings. I don't know whether they are applied in India yet or not, but here most of the vehicles, you will see that the coatings are there, all the BMWs, Mercedes, every German car as well as US car, latest cars have that coating. So that is very popular.
Okay, sir. Thank you.
Sure. Can you identify also when you ask question from which institution or industry, or just as a curiosity?
Yes, yes, sir. I am Professor Prem Joshi from Father Ragnar Polytechnic, Navi Mumbai, Vashi, and I am working as a lecturer in Mechanical Engineering Department.
Oh, great. Actually, my nephew just graduated from your school. He's in Vashi, correct?
Yes, 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 sir.
Yeah, and he is now here working for General Motors.
Yeah,
So
thank you, sir.
interesting. Yeah.
Yes, sir.
Sir, there are few questions in the chat box. If you
Yeah,
can
I'm
read
trying to
and
look.
first, yeah,
Let me
please.
see here. Let me see what are the questions.
Hello, good morning, sir.
Yes, Dilip
Yeah,
Kote.
yes,
Yeah.
sir. Good morning, sir. I'm Dilip, sir, from Andhra Pradesh, KL University.
Okay.
I'm working as assistant professor in mechanical engineering.
Uh-huh.
So my question is like, what materials we can choose to avoid the heat and moisture on the transparent surfaces? Let us say if you take car windshield, the windshield should not absorb heat as well as it should not absorb moisture. So I would like to prepare a nano coating. So which materials would be more feasible for that
So
application?
it has to be a basically transparent coating
Yeah,
because it's on windshield, correct?
yeah. Windshield or building elevation glass.
Correct. So basically they have tried three different. If you look at the titanium oxide, they have looked at that, and then I can look into what exactly they have used, because I haven't worked in that area, but I can get that information if you contact me directly. I
Sure,
can
sir,
get
sure.
it to you. Yeah.
Actually, I'm planning to do my PhD in the nano coatings area.
Oh, I see. Okay.
So I have already
So
started working on that, and I am doing the literature survey for that.
okay.
So
Great.
it would be great
That,
if you can
that
help me in that.
Oh, absolutely. And that's very interesting area,
Yeah.
very upcoming area in the nano coating. Actually, Dattaji, if Ram Mohan is going to talk.
Yeah. He agreed to deliver the morning session on Thursday.
Okay.
So
I will tell him to address some of, because he is working in the nano coatings. So I ask him to give a little bit more specific devote on nano coatings.
Sure, sir.
okay, sir.
Thank you, sir.
We will definitely look forward from him.
Yeah.
Can I have your email ID, sir, so that I can mail you my query?
Dattaji will, I can just put it in chat box
Okay.
here.
Thank you, sir.
It's simple, Kelkar at, let me, I put it in chat box.
Thank you, sir. Thank you very much.
Yeah. So how many of you are, I'm just curious that there is at least some aspect of nanotechnology in your curriculum, in your schools at undergraduate or graduate level, or trying to introduce?
Yeah, mainly we deal with materials, sir. Most of
Okay.
the time we deal with composites, metals. We used to
Okay.
tell the properties of the materials, properties of the nanotechnology, nanomaterials.
Okay.
But we don't go in deep into the preparatory level, like how to prepare that materials, what are the experimental setup required.
Do you
That
guys have like,
practicality is required, sir.
okay, so you don't have, because there are a lot of safety concerns also when
Yeah,
you
yeah.
deal with this nanotube, because you need really special, the labs where they're secluded, because if this carbon nanotubes or anything gets airborne, it can be fatal to the, students, and if they inhale, we don't know how bad they can be. So you have to do it really, really carefully. So there are also even in US not many labs where these things are handled. So slowly it's coming up. Great. Sorry, it's 1 o'clock early
Yeah.
morning here, almost.
Yeah, sir, we will take the remaining question through the
Take
email,
question
and
and
I will
send it
send.
to me.
Yeah, I will send
Yeah.
because it is too late in the US night. So once again,
Uh,
thank you, sir, for taking your time and spending to the late night, and sharing your entire research and enrich the knowledge of the nanotechnology, nano engineered material from the various laboratories of US and other countries, and from the JSNN. So really, this was one of the good presentation on the nano materials and the prospective way of using for the development of the existing material. So I take definitely our all the participant will take away maximum from this session as a nano material enrichment for the existing properties of the conventional material. So with these few words from our side, I think we shall give the thanks to again thanks to Dr. Ajit Kelkar sir for spending the late night time. So thank you so much, sir, from
thank and
on the
thank
behalf of VJDI,
Sure.
Department of Production Engineering, and AICT Atal FDP Learning Academy. I take this opportunity to thanks once again, and the session is closed. Thank you,
Great.
sir.
Thank you very much for everyone for it.
Thank you, sir.
Thanks. Have good night or
Good
good
night,
day
sir.
for
Take care.
it.
Yeah,
Yeah.
good night to you, sir. Take care, sir.
Yeah. Bye.
Yeah. Bye, sir. Bye. So participant, the next session would be scheduled through the same link, and the next speaker will be joining for the session is our his name is Dr. Kiran Bhole. He will be talking on the lithography. So all of you are requested to join on the time to attend the session. Fill up your attendance come feedback form for the every session, and send your responses. In case of any difficulty, the Professor P.R. Attar will reply you back on filling the form for the feedback come attendance. Is there any kind of query or any kind of doubt? I can give 2 more minutes, and then I will close the session. Any concern, any query?
Sir, are you going to share the PPTs of the speaker or the videos or something?
Video would be a link will be given. You can watch it. Video cannot be shared because each session is almost like 800 to 900 megabytes. So MB is, so for the entire session, it could be around like 10 to 15 gigabytes. So it is difficult depending upon whatever the PPT is coming as a shareable PPT in terms of PDF file that I can share to the all participants. Those who have attended, those who are not attending, they have been approved. So it is very sad to say I approved the 200 people who registered, and out of that only I can see on the screen 128 max to max. Remaining people, they unnecessarily block the seats of the others. So being an academician or being a faculty, you shall be a very much ethical about attending such kind of program also, because other people, they are continuously calling till the last day of the program, and I unfortunately could not admit them even they had a wish to attend such kind of program. So kindly I appeal all the participants, if some of your colleagues are not attending the session, tell them to attend, otherwise they may not get the certificate if they won't fulfill the criteria of the attendance 80%. So these are the few notes from my side, and we will join for the next session. If you have any query and concern, I will give 1 more minute, otherwise we can close today's morning session.
Okay, sir. Thank you.
So once again, thank you one and
Sir,
all. Yeah.
sir, can you kindly connect me with that faculty what whom Kelkar sir has told one name?
You can he gave the email address. If you have your own doubts and some kind of queries, you can shoot an email to him, and he will be reply you back. And another speaker from the North Carolina State University, Dr. Ram Mohan, is going to deliver his expert talk on Thursday morning. So he will take few of those questions what he has not been answered today.
Sure, sir. Thank you.
Yeah. So with these notes, I'm closing the session. Thank you all.
Body, various systems of the body. So this is one more application apart from the automobile or the industrial application. So there are plenty of these things. Now, so coming to this, my topic, very first, I will be discussing on the microstereolithography system. As I said, it is one of the microfabrication process for the MEMS, for the micro electromechanical systems, and it is the subset of like additive manufacturing process, where we build the device one layer by layer. Okay, so this is how we are going at this particular process. Just look at this particular this schematics, and we can get a clear idea how the components are getting fabricated using this micro stereolithography process. In short, I will call it as MSL. Okay, micro stereolithography. In short, I will call it as MSL. So in this MSL, first of all, we are developing a CAD model. So CAD model can be developed in any CAD modeling software, such as SolidWorks, we have CATIA, or we have the Autodesk, and so and so. So there are different CAD modeling softwares. We can develop very first a CAD model of it in the computer. Okay. Next, what we will do is, as I said, this is the additive manufacturing process. This is a 3D printing process. So this CAD model 3D structure which we have to generate or which we have to fabricate, we have to slice it and get generate, and we have to generate the number of 2D components out of it, or 2D structures out of it. So what we required is nothing but a slicing planes. So we can cut this we can cut this 3D object. So with this slicing plane, as I have demonstrated here, the one CAD model which is which resembling a cone type of structure, and these two are the representation of the slicing plane applied to it. And when we cut it through this slice plane, then we will get the number of circles which are the outcome of the 2D structure from as outcome from the 3D CAD model. So still we are in the computer. We are doing everything the process in the computer. We are developing a CAD model, and then we are slicing it, and after slicing we are getting the number of such 2D structures. Okay, so this 2D structure we have to fabricate in layer by layer way. When we fabricate this in layer by layer way and pile it one over other, then we are going to get this structure, 3D structure. So this is what we have to realize in the fabrication. Okay, this is what we have to execute in the fabrication. Okay, so what we required is in typical line scanning MSL process, which is of our interest when we look at the high resolution point of view, like a micrometer or in nanometer also we can go. So in that aspect point of view, we are going for the line scanning type of the MSL system. So once we get the 2D layers developed, then we are putting the line scan and getting the data. Now for what purpose we are getting this line scan and how we get the scan for data, so that we'll discuss again. We'll come back here after a few discussion on the physical process, how this fabrication takes place. Okay, so when we have sliced it and we have generated number of 2D planes, these 2D planes we have to fabricate in actual system. And when we piled up this 2D plane, then the integrated or the object is nothing but this 3D component. Okay, that is the CAD model which we have prepared for the fabrication. So how we do that? So we are having a laser source here in typical in MSL system. Typically, we use the arginine laser. The wavelength ranging from the 351 to 375 nanometer. We can use the any other laser also, Nd:YAG and the CD and all that particular laser. But typically, in most the of the resins available in the range of photosensitive to in the range of UV range of the 351 to 375. So we are preferred with the arginine laser here. and this argon ion laser then emits the laser beam, and then we are having the optical switch here. The basic function of the optical switch here is to make the laser on and off. Okay, so when the optical switch is on, then it passes this laser for across it, and then it falls into the mirror. Mirrors are mounted on XY scanner, and then from the XY scanner, this laser beam is passed to the focusing lens, and the focus beam is on the photopolymer resin, which is kept in a tank here. So we are having this yellow color as a photopolymer resin, and initially what we are going to do is this particular jet platform which we are having in a tank. This is a build platform. This build platform is kept very close to the resin surface. So a thin layer of this resin surface is on top of this build platform initially. Okay, and then we are scanning this laser beam through the scanner. So mirrors are arranged on the scanner, and the mirrors are moved, and then when mirrors are moved, this focus beam also gets scanned, also get moved, and it is moved, and wherever it is falling onto the resin, there the photopolymerization gets triggered, and when there we get this liquid polymer or liquid resin turned into the solid part. So this is what we are going to do in fabrication of one particular the 2D structure. So when this build platform is very near to this resin, we are scanning this first layer, and when we are scanning this first layer, the wherever the laser gate falls, the photopolymerization gets triggered, and then as an outcome of that, we are getting the 2D component getting developed over there. So this scan path is nothing but the scan path of the laser. This scan path is nothing but the scan path of the laser. Wherever this this line indicates the path of the laser, wherever the line is within the circle, that is the part which we desire to fabricate. I'm talking in perspective to this particular structure which we have obtained by as an outcome of the slicing plane, by outcome of the slice from this 3D component. So when wherever this line is within the circle, that is of our interest. So the laser should be on during this part where whenever it is within the circle, and the laser should be off whenever it is passing outside the boundary of this particular circle. Okay, so that's why this optical switch is meant for that. So we need to have the scan path, and from this scan path, what we are going to get the data is nothing but the laser XY position and the laser on off data. So these are the data which are essentially required while fabricating this structures to this structure. So initially we are keeping this build platform very close to the close to the resin of the surface of the resin, and we are passing the first scan part data for the first circle to get developed, and this data consists of the laser XY position as well as laser on off data. So when we are passing this data, then we are going to get the first 2D structure developed. And when first 2D structure is getting developed, then after that this build platform is dipped into the resin, a fresh layer of liquid comes over it, and when fresh layer of liquid comes over it, again the second scan part data is fed through a microcontroller to the system, and we can get the second scan part, the second layer fabricated. So this way we are going one layer by layer process, layer by layer way, and the entire 3D structure can be fabricated using this particular process. Okay, so this is how this particular MSL system works. Now there are some of the very important points where I would like to keep your focus attention, that this particular component in microstereolithography we are developing in sizes in microns. Micron sizes means like 1 micron to the microsystems or microstructure fabricated in the range of the size. Size ranges from the 1 micron to 1,000 micron, and that's gives some of the challenges in the system, as we are having the XY scanner. So XY scanner, if we have to fabricate a micron size, then XY scanner need to have the accuracy in nanometer. Then only it is possible to fabricate the structure in in micron size. Otherwise, if you look at this particular scanner, and the scanner is supposed to generate a straight line, but that straight line need to be having accuracy of nanometer range or nanometer size and intolerance of nanometer. And if we deploy our conventional straight line mechanisms, then which consist of the linkages or rigid body linkages, and the rigid body linkages connected with the pin, and the pins may have the clearance in microns, so that will not that cannot solve the purpose. Okay, because if we want to generate a straight line for a size of this circle of 500 micron, then this has to be in nanometer. Otherwise, if the pin joint type of the structure, if we want to fabricate, then we may start from this end, and instead of this particular perfect straight line, we may get the line or the point over here. Okay, and that will not solve our purpose. So there are few challenges if the micrometer sizes structure are to be fabricated. The scanner need to have accuracy in nanometer range. Then only it will justify its application in the development of the microstructures, right? So this is how the component is getting fabricated, and I'm also focused on what are the challenges involved. Another very important point is that the laser light which we are going to use in this particular system is having the Gaussian energy distribution. This is the Gaussian energy distribution that we have, and the resin which is used, the photopolymer resin which we are using in this particular system, will be will get polymerized only if the energy delivered by the laser beam is beyond some critical energy of the photopolymer resin. So photopolymer is having some properties like after some critical energy only, if the energy is exceeded after some critical energy, which is called as the yield energy for the resin, also called as yield energy or the threshold energy for the resin, then only the photopolymerization is going to trigger. Photopolymerization will not get trigger at any energy. It will get trigger only after the energy pass through this critical energy or the threshold energy. Okay, so we are going to get when we are having a Gaussian laser intensity distribution, the curing will take place only after the certain amount of the energy. So the line which we are going to get will be having some Gaussian distribution along the width, and that Gaussian distribution of the width is also like here shown here. So Gaussian shape we will be forming here when we are scanning the laser beam onto the photopolymer resin. So this is the cured depth and this is the line width. We can see here this particular line segment is not a rectangular. It is a Gaussian part of the Gaussian part, I mean top part of the Gaussian beam. So it is very important that the layer thickness in the process need to be very small, then only we can get accurate component, accurate or high resolution component. Now another, the point or the disadvantage in this particular thing having the minimum layer thickness is that the minimum layer thickness will yield lot of like time consuming process. It is a like I mean if you have the minimum layer thickness possible, then the number of these scans can be more, and thus at the minimum as the number of scans are more, it will take a lot of time in fabrication of the entire 3D component. So the time required for the fabrication will get increased. Okay, another challenge in if you are going to have a compromise with the time, you don't have like the time as a constant. You can go. You want like the highly resolution component to get produced, and time is not you are not constant. Then the what is another challenge is that the keeping the minimum layer thickness is not possible if the uh, if the viscosity the viscosity is too high of the resin. We can imagine that when we are dipping this particular platform into the resin and the viscosity, if it is very high, then it will not flow over the platform very easily. It will build onto the edges, and after certain depth is achieved, then only this particular resin will flow over the build platform, and thus it will need some kind of a threshold to reach, and after that only, as the resin is going to flow over the build platform, so that gives the limitation on the layer thickness. So these are various challenges when we are going to fabricate the micro components in using the micro steady lithography process. And these challenges are not there where we are fabricating the micron size, meso size component, or the component ranges in millimeters or in centimeters, like in typical additive, normal additive manufacturing processes. But when we are going to process with a micron size component, these are some of the challenges that we are going to face in the fabrication. So we will discuss here in my presentation what are the how the systems get evolved, how the systems get designed for to overcome all these particular challenges present in the micro fabrication. So I will come to that particular point after the one more slide over here. So what are the different types of the micro stereolithography system? One is the constant surface technique. In constant surface technique, what we are going to do is we are going to have one more the transparent substrate here, and then laser is passed through that transparent substrate, and the liquid layer is sandwiched between the transparent substrate and the build platform. So this will counter the phenomena due to the high viscosity of the resin, and the minimum layer thickness can be addressed or can be achieved. So this is the benefit of the constant surface technique. And the constant surface technique is having the one practical limitation is that when the laser is passed through that particular the transparent substrate, that particular and the layer may stick to the topmost the bottom layer of the transparent substrate, and thus when we are going to build the next layer component, that will make the hindrances, and that's why that is one of the limitation in the constant surface techniques. Though some of the researcher has come with a solution that they can give the oxygen plasma treatment, and then they can get rid with that sticking problem, and can fabricate the component of high resolution. And the another technique is the free surface technique, which I have demonstrated here in the slide. So this is a free surface technique typically used in the MSL system. Another is the integrated micro stereolithography, or LCD or DMD type of the micro stereolithography process. In LCD or DMD type of the micro stereolithography process, what we are having is the entire the component, entire 2D structure is fabricated in one exposure of the laser beam. Okay, so rather than line by line scanning, we are having entire projection of the entire 2D structure. Okay, so for that we required liquid crystal display or the digital micromirror device. So to get into this, it is very similar to our projector type of thing. Okay, the overhead projector that we use. Okay, the 2D screen is the projected onto the wall, right, in our projector. So like that, the entire 2D structure is projected onto the resin surface, and that entire 2D structure is getting fabricated in one shot in this type of the LCD and DMD type of the micro stereolithography process. So eventually this is very fast process, because rather than like scanning line by line and getting the one 2D structure developed, we are focusing that we are exposing the entire 2D structure in one go, and so in lesser time we are fabricating the component. But the resolution is a matter. Resolution is a problem. We cannot get the high resolution in the LCD and the DMD type of the micro stereolithography system. So for high resolution we have to go for the line scanning type of the FSL process. So these are the various types of the microstereolithography process that we are having here. One very important point which I have mentioned is that the microstereolithography system, wherein we have to generate a component in micron size. So scanning mechanism need to have accuracy in nanometer ranges. And so the scanning mechanism cannot be built based on the conventional straight line mechanisms that perhaps we have seen in our the curriculum of the theory of machines and all. So that a conventional straight line mechanism, which consists of the two rigid bodies connected by a pin, and the pin is having the clearance in something in microns, that cannot be used, because if the clearance is in microns, the error is going to be in microns, and the component which we are going to fabricate is in micron. So if the error is in micron and component needs to be fabricated in micron size, this combination is not going to work. So conventional straight line mechanism is not a solution for the scanning purposes in case of such microstereolithography system. We need to have the scanning mechanism of high resolution. That resolution should be in nanometer. Okay, so what are the various techniques the people have come across for the fabrication of this component? Let us have that particular look here. So first scanning scheme is nothing but the post objective scanning scheme. Here in post objective scanning scheme, we are having a laser beam coming from the laser source, and then first of all we are having a lens, and then the two mirrors M1 and M2, and this M1 and M2 are tilted. When this M1 and M2 are tilted, we can get the motion in X and Y direction. So this is how we are going to get the motion in X and Y direction, by tilting the mirrors M1 and M2. So the scheme we can use for the smaller component, so small range size component, but cannot be employed for the large size component, but definitely we can use for the smaller size component this particular scheme. The reason is that why we cannot use for large size component. The reason is that the laser beam is not focused, cannot this focus cannot be maintained for larger range. It is logical that from the when the beam is coming from the lens and falling onto the mirror, the focal point will be one and only one, at one and only one place. When we are tilting at other places, it will be defocus point. I will navigate to this particular the slide over here. We can see here, this is the mirror. Laser beam is coming and falling onto the mirror, and then laser focus will be somewhere here. If we tilt the mirror, this is the scan path or focus, locus of the focus of the beam. So focus is not onto the resin surface. It is defocus. Whatever we are getting on the resin surface at other points other than this particular point or this region is a defocus beam. Okay, this is the locus of the focus, and we can see on the resin then it is all over the except this two particular point. Maybe at all other points it is a defocus beam. So as it is defocus beam, resolution cannot be achieved. We need for high resolution, the focus beam need to be scanned all over the range. So as it is defocus, the resolution cannot be achieved. Or else we can say we can use this scheme, but only in the region where the focus beam is moderately achieved. So that range is very, very small. Okay, so we can employ this scheme for small size component, for very, very small size component. But if we want to fabricate, let us say, a component which is ranging large, but resolution is needed is very high. Let us say a 5 micron line for a centimeter long. So we cannot fabricate that. So that is the limitation of the post objective scanning scheme. Then we are having the pre-objective scanning scheme. In pre-objective scanning scheme, laser beam again coming from the laser source, falling onto the mirrors M1 and M2, and then from M1 and M2 going onto the focusing beam over here. And then focusing beam focuses the laser beam onto the resin surface here. Mirror M1 and M2 are tilted to get the X and Y direction. So beam to go in X and Y direction, we are having the mirrors and then the mirrors M1 and M2, which can be rotated. Again, the similar problem which we have seen in post objective can be observed in pre objective. The focus spot do not remain constant throughout the scan surface or throughout the resin surface. The focus beam cannot be maintained, and thus we cannot use this particular scheme for large range component of high resolution. That we cannot use. So this is the limitation of the pre objective. Third scheme the people have come across is the off-axis laser scanning scheme. So we don't have the mirror over here. We directly have the source, and the source can be moved onto the focus beam here. And in this way, we can have the X and Y direction, the beam going into the X and Y direction by moving the laser source directly onto the focusing lens. But again, we can see that the focus beam the beam get distorted and do not remain focused in this case as well. So that is again the similar problem that we'll face in case of the what we have faced in the case of the post objective and the pre-objective scanning scheme. Next scheme is a photoreactor tank scheme. Here, this laser source and focusing lens is constant. They do not move. Rather, what we are moving is the photoreactor tank. So as the focus spot is constant and the reactor tank is scanned, we can very well achieve the focus point all over the resin surface. So this is possible. So this was not possible in earlier scheme. That focus beam was not possible on on all the resin surface. That do not come as a problem here in this particular scheme, that is the photoreactor tank scanning scheme. So as because we are having the laser beam and the focus beam focusing lens, and then focus spot is maintained on the surface, and now this is not moved, as this is not moved or not tilted because of the mirror is not at all present over there. So we can now move the photoreactor tank, and because of this movement of the photoreactor tank, the focus beam remains all over constant. All over the surface, focus remains constant. So that is the biggest advantage of the photoreactor tank. But what are the problems? When we are scanning the tank, there in a tank we are having the resin surface, liquid resin surface, and the waves will be formed of this liquid surface, and thus it will not again make the structure of high resolution. It will create the wavy microstructure because of the motion of the resin which is in the tank. We are moving the tank, and because of the movement of the tank, there will be disturbances and the wavy structures can be formed. And thus, the component of high resolution is again a limitation in this particular case. Okay, we can have the focus beam on the surface, but we have the limitation on the motion or the velocity magnitude. We cannot move the tank of whatever motion or whatever the velocity. If we move with high velocity, then there will be the creation of the wavy structures, and that is not of our interest. So these are the some of the scanning schemes which are there in place for the fabrication of the micron size structures using the microstereolithography or the MSL. So what we can see through this simulation as well. So that is logical what we have discussed so far, and through the simulation also that is verified. We can see that the intensity at 0, 0 is peak. Intensity at 0, 0 point is peak where the focus is on the resin surface. But when we move across some distance by using off-axis scheme or post-objective or pre-objective, then it becomes a defocus at all other region. And because as it is defocus at all other region, the intensity get diminishes quickly. We can see that intensity is quickly diminishes, and we can see through the simulation result over here as well at the bottom that intensity get diminished quickly in all the scheme like pre-objective, post-objective, and off-axis, and thus we cannot achieve the high resolution component because the focus is the focus is no more constant all over. It is defocus beam in the another region other than 00. So 00 point at all other region there is a defocus part, and thus it will be a broad laser beam, a larger laser beam, and we cannot achieve the high resolution structure over here. So this is proved using simulation. It is logical as well, but it is quantified through the simulation, and we can see like even for a distance of 500 micron or 1000 micron how the intensity get diminished very quickly. You can see this intensity here. This peak intensity is around to 3.25 in magnitude, and it diminishes quickly at 1 mm, that is 1000 micron, quickly to zero point 0.5 or up to 1 magnitude of the intensity. So this is the problem associated with the all these particular schemes. Okay, so now what is the solution for that? How we can fabricate a large range component but high resolution. Large range component means I want to fabricate a line of 5 micron, but ranging from length ranging from the 5 centimeter or 10 centimeter, something like that. Like if we want to fabricate on a PCB printed circuit board some line and all, so how we can do that? You know how the small lines which are ranging in large in dimension, but resolution is very small. Resolution is very high. I mean, sorry, resolution is high. So how that we can fabricate that particular such lines? So that is the question. So how we can go with the different schemes that we will explore through the one novel scheme that is called as the on-axis optomechanical scanning. So this is what actually is developed in the IIT Bombay laboratory where I have pursued my PhD. So I will be discussing all that. So what we are going in this on-axis scanning scheme is we are having a laser beam. Laser beam get falls onto the mirror M2 and then M1. So these are the two mirrors, and then we are having a focusing lens over here, and the laser beam get focused onto this focusing plane where we are having the resin surface. This is the y direction, this is the x direction, and we can see this is the z direction. How we can make the focus constant all over the resin surface, that is demonstrated here through this one particular animation that I would like to show to you. So what is done in this on-axis scanning scheme is, let's look at this animation. So first part is this M1 along with the focusing lens is moved on this axis. The laser beam is coming from the laser source, and then we are having the laser beam passed through from the M2 mirror onto the M1, and then the focusing lens. When we are moving in y direction, M1 along with the focusing lens is moved onto this axis. So when it is moved onto this axis in this way, the focus remains constant in the y direction, right? The focus remains constant in y direction. Now further, now you can see if it comes backward again in the same way, then focus remains constant in the y direction. And you can go whatever distance, whatever centimeter, millimeter, whatever the distance. You can, if this scheme is employed, then focus do remain constant in y direction. What about the x direction? If we want like this to execute the same in the x direction, then this M1, M2 and lens has to be moved together. So this when M1, M2 and lens total move together on this axis, this particular axis, the axis of the laser beam coming from the laser source. When M1, M2 and focusing lens all together moving on this axis, then the motion is in x direction, and in x direction as well, we are going to get the focus point all over constant. Okay, so this way, this scanning scheme typically is the on the axis of the laser beam. So in for x direction we are moving M1, M2 and focusing lens in this on the axis coming from the laser source, and for y direction we are moving the M1 and focusing lens on the axis of the laser beam coming from the M2. So with this, The laser beam is we are able to keep it focused on the x in the x and y direction for whatever at whatever the location, and that's why this is the state of art on axis mechanical scanning scheme, which can be used for the which can be used for the fabrication of the component of large size and high resolution. Okay, and we can see that the resin tank is stationary, so there is no waving structure in this scheme, and high speed of scanning is possible as well as compared to the photoreactor tank scanning scheme. Let us move. So, how this scheme is again simulated along with the another schemes, and this simulated results are shown over here along with the other scheme. So you can see the D is the shown over here is the on-axis scanning scheme. So D is the on-axis scanning scheme, and ABC, these are the pre-objective, post-objective, and off-axis scanning scheme. We can see here when we are moving the laser beam across the any distance, like distance from 0 to 4 mm on one side, minus 4 mm on another side, means like plus or minus 4 mm on plus or minus 4 mm, then we can see that laser spot size is almost constant in on-axis scanning scheme. Laser spot is almost constant, but in other cases, as the laser beam is defocused, the laser spot size is very big. We can see the big laser spot size. Okay, so this can see early here the laser spot size is very big in all other scanning schemes. Similarly, if you look at the intensity is almost constant in case of the on-axis scanning scheme. Almost for the range of plus or minus 4 mm, it is a constant throughout the range. But in all other cases, we can see like in ABC cases, the intensity get diminished because it is not constant, it is defocused, and as it is a defocus, the intensity diminishes, and intensity is very small, and we cannot even cure sometimes the photopolymer because it do not like goes to beyond critical energy of the resin, beyond threshold energy of the resin, and thus the curing will not take place. We cannot fabricate the structure at that particular intensity when it is a defocus. So these are the some of the problems, and thus we can see that the on-axis scanning scheme is very promising scanning scheme, and we can fabricate the component of larger size using this particular scheme. And this is the now how based on this scheme the mechanism is fabricated. I will show some like the glimpses of the mechanism, and I will discuss the mechanism which is fabricated. The concept is okay, but how do we realize that, how we do practically implement that, we will see. And after practical implementation, these are some of the results shown here, that the how the experimentally obtained and this experimentally obtained simulation and experimentally obtained results and the simulation results do match, and we get the spot size constant, then the intensity also constant in both experimental and the simulation. We can see some the simulation and experimental profile of the beam here. So this is the simulation profile, this is the experimental profile, and we can see the profile is almost showing that the beam profile is almost constant, and it is focused, showing that it is a focused beam at the any other point other than 0 0. So this is shown over here. Now I will take you to the mechanism build. So this scheme is okay, we have discussed scheme, that on axis scheme is having a potential to maintain a focus spot for wide range of the scanning, and thus we can use it, or we can use or deploy it in the microstereolithography system. But how we can do that? As I have mentioned already, if you use conventional straight line mechanisms which deals with the rigid linkages connected by the pin joint, and the pin joint itself will have the clearance in micron, and if the clearance is in micron, errors will be in micron, and if the errors is in micron, we cannot fabricate the structure which are in micron size, ranging from 1 micron to let us say 1000 micron. Forget about the nanometer size structure. Okay, so we cannot fabricate the micron size structure even. So with this conventional mechanism, so we have to go across some mechanisms or some strategy which will fabricate which will give the scanning resolution in nanometer scale. Okay, so one thing is clear, we cannot use the conventional mechanism. So how we can do that? How we can execute on-axis scheme? We have proposed, we have seen on-axis benefit of the on-axis scheme, but how practically execute that? With what mechanism to execute that? That is a big question mark over here. So this to execute this, the idea has taken from the CD-ROM, and the in CD-ROM we are having the laser beam, and that laser beam is scanned over the CD or the DVD surface and to pick up the data, and we can see the data and all. So the mechanism used in CD-ROM is a flexural mechanism, and that mechanism used in CD-ROM is having the nanometer range accuracy, and that's why it is employed in the MSL scheme in the microstereolithography system. Okay, what is that particular mechanism? That mechanism used in CD-ROM, that is the motivation, that is taken from there, the idea is taken from there and implemented in this 3D printer over here. So what is that mechanism consist of? So that mechanism consists of the 4 linkages. So here the linkages shown here, B1, B2, B3, B4. You can very well open the CD-ROM if you are having, and you can see this particular mechanism in place over there. And that is the mechanism which is used in the MSL system as well. So there are 4 linkages, B1, B2, B3, and B4. And this 4, out of these 4 linkages, the outer linkages, that is B1 and B2, are fixed here at this point, S1 and S2. So these are the fixed point, S1 and S2, and all 4 these flexural linkages, flexible linkages. These are not rigid body, these are the flexible linkages, do remember. Okay, so these are flexural body. This is a flexural body, it can bend easily, it is not rigid body. But this all 4 linkages are connected rigidly here at the end. So this is a rigid body, and this B1, B2, B3, B4, all these are the flexible bodies. Okay, and outer linkages are fixed over here. These are fixed over here. All these flexural linkages are connected rigidly at the end, and the force is applied here at this particular segment. So this inner linkages are connected to the body, connected to one particular body or rigid body over here, and the force is applied to this particular the body here. And when this force is applied, this B1, B2, B3, B4, they get deformed, and they deform in such a way that this deflection delta is always in a straight line or always in the direction of the application of the force F. Okay, so that is the beauty of this flexural mechanism, and this is first of all invented by the Shaurya Avatar at MIT USA, and he has patented it, and then it is used in the CD-ROM, and then after it is successful deployment in the CD-ROM, and the same is used in this MSL system developed at the Suman Maslow Advanced Microengineering Laboratory of IIT Bombay. So there we have used this particular, I mean this Dr. Suhas Deshmukh in his doctoral work, he has used this particular concept and developed this 3D printing. So this is the central idea about the flexural mechanism, how we can use for the accurate motion. So this is the picture of the system which he has developed. So these are the flexural linkages that I'm talking about. So this is the link 1, 2, 3, 4. This outer linkages are fixed here. You can see like these are firmly fixed to this black body over here, and all these 4 linkages are connected to a rigid body, that is the acrylic body over here, placed here. So this is the acrylic body, the fixed rigid body. All 4 linkages are firmly fixed to it. Outer linkages are connected firmly over here, and this inner linkages are connected to this central body over here, and the force can be applied to this particular body using this actuator. So there are 2 set of this flexural mechanism. One is this set, another set is this. So we are having 4 linkages here, 1, 2, 3, 4. Outer linkages are fixed over here, inner linkages are connected to the body over here, and that on that body the force is applied using this actuator mentioned over here. This is a voice coil actuator which we are having here. Okay, so this one flexural mechanism is for one in one the motion for one of the motion in 3D printing, that is, let us say X, and another for Y. So this way we can have the XY scanner for this 3D printer using this flexural mechanism. Another very important is that the flexural mechanism, as I said, when we are applying the force F onto the inner flexural linkages, it deform, and the deformation is in such a way that that deformation is in exactly straight line direction as in the direction in that of the force applied onto that linkages, that is a force F, and in that direction of the force F the deformation we are getting, and that is a very accurate deformation we are getting over there. Now, apart from this, we must have, as there is a no pin joint over here, the deformation is very straight line, and this deformation is the outcome of the flexural part, or because of the flexibility of these the linkages that we are having. Now, another important part is whatever the actuator we are having, the force coming from one of the actuator, that force coming from the actuator also need to be in one direction only, right? So for that, the voice coil actuators are implemented here in this scheme. So voice coil actuator is because of the magnetic levitation, we are having no friction, and we get the force in one linear direction only. I mean, in the perfectly in linear direction only, and because of that the flexural linkages also tend to give the deformation in the in that particular prescribed direction of the force F. So this is how this entire system is built for this 3D printer. This scanning system is built for the 3D printing. Let us look at the optics what we are having in the on axis MSL. So we are having laser source, Argara and laser source, as I said. Then AOM, acoustic optical modulator, that is nothing but the optical switch. The function of the optical switch is to make the laser on and off, and it makes the 3 degree beam to pass through it. 1 degree is passed across the pinhole, and then we are having the M3 and M4 mirror. This is for adjustment. Initially, if we have some error in the fabrication, then that to counter attack on that particular error. So this M3 and M4 mirrors are placed. Then M1 and M2 mirrors are on scanning mechanism, that is a flexural scanning mechanism. And from this M1 and M2, we are having the laser beam on the focusing lens, and then from the focusing lens, laser is focused onto the resin surface. So this is the optical scheme used for the MSL purpose, and these are the direction in which the mirrors can move. This is the design scanning schematic design of the scanning MSL system as a total MSL system. So we are having a computer CAD data. So this CAD modeling software and all the data can be processed using the computer. This is the like for making the model, slicing, and generating the data. So this this computer is connected with the microcontroller. So the microcontroller used in this MSL system is the DS1104, which we have used. That is a German make, mostly used in automobile sector. And we get this data scan part data, that is the XY position of the laser beam, and the laser on-off data that is given to the system through the microcontroller. So this optomechatronic system gets the data of X and Y data at particular time t, and the microcontroller gives the data of laser on and off with respect to time t to the optical switch, that is acoustic optical modulator. They work in a sync and gives this data, thus we can get the fabrication of the layer by layer way of the components. So this optomechatronics system moves in X and Y direction and supplemented by the data of laser on and off, and thus we can fabricate the layer by layer way all the component, and thus when we stack all the component, we get the entire 3D component getting developed. This is the entire system, photograph of the entire system developed at Suman Masol Advanced Microengineering Laboratory. So we are having laser source over here. So this is the arcanine laser source. This is the physical picture of the acoustic optical modulator or the optical shutter, optical switch, and then we are having the M1 and M2, M3 and M4 mirrors, and from there we can go ahead for the pinholes, and then M1 and M2 mirrors are arranged on this flexural mechanism. This flexural mechanism picture already I have shown to you, and then we are having the bill platform and all that here at the bottom, and this entire the fabrication can take place here in the tank region at the bottom. So this is typical the output of the software that it is developed in house by the Mr. Amit Pathak and Aram Baraki during his entire MTech work at IIT Bombay. And this is how we can get the 3D CAD data, the scan part data, the laser on-off data, and XY focus data as the outcome of indigenously developed the software package. It is developed in the MATLAB. And then this is the system integration. We are having the CAD computing system, and then the microcontroller. As I told you, it is a DSpace 1104 platform, DS1104 platform. This is a microcontroller as well as the data acquisition system, and there are various channels, digital to analog converter, and then the encoder channels. So we can see that we can give the data to the DSC channel for the X stage, for the Y stage, and thus the XY mechanism moves, XY flexural mechanism moves. The real time data of the XY stages is taken from the encoder connected to the system, and that encoder gives the data to the microcontroller acts on it, compare it with the scan part data, actual scan, the scan part data, idle scan part data, and the PID controller works onto it and gives the data further to the DSC, and then in this way it is a controlled motion is achieved. Then DSC channel 3 is connected to the RF driver, which gives the signal to the acoustic optical modulator for making the laser beam on and off as per the desired thing. This is the hardware, which is hardware and power supply. These are the RGF and interpolator, which is taking the data from the encoders. These are the power supply, and this is the RF driver for the optical switch. These are the current amplifiers for the voice coil actuators, which are employed, and this is the CLP board of the DSpace 1104 platform. So this is the all the hardware which is there in this particular system. Now if you see, now the latest version, I don't have the latest version picture of the system which is developed at the in the laboratory now, but you can see now this entire hardware has gone, and now it is completely embedded, and you can see the entire 3D printing 3D printing process, this entire 3D printing process on in a scale of on a scale of like laptop. You can like such a small miniaturized system is developed now. This is the some of the videos I can show you. If it gets played over here, we'll try it. Yeah, it works. So this is the how the mechanism is moving. You can see this is the voice coil actuator, and the mechanism is moved in y-axis. So it moves in perfectly straight line. This is for high speed. So first video was for at low speed, second video at a high speed. The same y-axis motion. Then this is the XY, both this high speed in X and Y direction both. So you can see here, this is the Y direction, and this is actuated with the actuator over here. So this is the voice coil actuator here. So this is for Y axis, and similarly we can see for the X axis as well. So this part is moving. So this is the direction in the X axis. So it shows like Y is also moving, X is also moving, and this blue line is the argon iron. Blue shade is of the argon iron laser, which is falling onto this mirrors M1 and M2. So these are the mirrors M1 and M2. And this is for high speed large range XY scanning, this last video. So you can see the motion in X and Y direction both. So this is Y actuator, and this is the result motion for the because of the X actuator here. This blue shade is of the laser beam coming onto the M1 and M2 mirrors. So these are the M1 and M2 mirrors. And we can see this is the high speed large range. Range is also large, and it is a high speed. So the mechanism is built and successfully deployed for the 3D microfabrication. So, as I said, it is very important that whether this particular mechanism is having accuracy in a range of the nanometer or not. As mentioned that we have to generate the component in micron, but the accuracy needed to nanometer, then only we can use it accurately in case of micron. Because in microstructures, microsystems, when we are looking at the fabrication of the systems in the range of micron, like gears and all these to be developed in some micron size, then really the assembly and for all that purpose the resolution need to be in nanometer. So we can see here, this is the data captured using the data acquisition software, and the as the mass is moving, the maximum error is possible at the corner, because then when mass is moving and turning in 90 degree, so your scanning mechanism moves like in this direction and turning 90 degree, then this is the point where the maximum error is expected. And we can see this is the enlarged view of this corner over here, and this dimension you can see here on your screen. This is minus 800.5, this is minus 800, means this particular distance is 500 nanometer, and then this 500 nanometer, this error is within the 500 nanometer. I mean something a fraction of the 500 nanometer, and something in the range of like 50 or 100 nanometers. Similar another point is taken over here, and we can see that this distance is 250 nanometer, and your the lines are within 250 nanometers. So it shows clearly that the mechanism is having the nanometer accuracy. We can see the exposition data while scanning the exposition data, and this is the corner point, and which is magnified in this inset. And again we can see that this distance is of 500 nanometer, and our error is within the 500 nanometer. Again, another magnified point over here in the inset for the Y position scanning, and in the Y position scanning also we can see that the scan the error in the scanning is within the 250 nanometer. So in fractions of the 250 nanometer, I mean few nanometers it is. So it clearly indicates that the mechanism built is very well suited for the manufacturing of the micron size component, and can be extended to the nanometer size component. Now there are few of the problems. I mean, from the scanning mechanism point of view, the fabrication, this can be extended to nanometer size component. But as it is as a system, if we look at, there is a it is a outcome of the photopolymerization process. So the one has to look at the photopolymerization constant as well, and because of that, perhaps this at presently it is in for the fabrication of microstructures. But if we can control the chemistry, then we can be extended for the nanometer size component as well. We can see for few scanned path data, the lines are scanned, and then these lines are observed under the optical microscope for the various near to focus distance, and then it is tuned to get the focus. So we have done this particular experiment near to focus distance, and then the focus distance is tuned. Although we get the focus point focal distance correctly given by the manufacturer of the focusing lens, but still when we are assembling it into the system, there will be some error, and thus this experiment are very important to do, so that we can tune and we can find out the best focus point in the process. So the best focus point in this, the number of such trial experiments are carried out, and we have obtained this focus distance over here. And the number of the experiments are done before fabrication of the entire 3D structure on this developed the microstereolithography system. So this is the CAD model of the structure, and these are the, on the right hand side is the fabricated structure. You can see in the CAD model, there are the different circles like C1 to C7. In CAD model, the dimensions of the circles are ranging from 500 microns to 50 microns. The bigger one given here is a circle of 500 micron dimension, and the smaller one, that is a C7 circle, is of the 50 micron dimension. And thus we are having the ranges of these circles in between. And then this CAD model is developed, and then it is fabricated using the machine which we have developed. And the 4 trials are taken, and after each trial the measurement is taken and the average is computed, and based on the average then the error is estimated. Okay, we can see that the average for the all like the different sizes of the circles are noted here, and the errors are calculated based on the average, and then percentage distortion is calculated. So we can see, if you go smaller the size, the percentage distortion is more, because this is the effect of the shrinkage that happens in the photopolymerization. So we need to overcome this problem of a shrinkage which is there in the photopolymerization process, and if we can control over that, then this error can be further reduced. So maximum distortion or maximum error, percentage error reported during these runs or trial runs is 18.45 here, and the minimum distortion percentage distortion is 1.33 for the sizes of the in the range of the 500 microns. Now, if we look at the another type of the structure, similar but another type of the structure, like we are having here in this case the circles which were hollow. Now these are the solid circles, the same dimensions 500 to 50, but these are the solid circles. These are the solid circles. Now circles are to be fabricated. Here circles were not to fabricate. I mean, the hollow part is of our interest, whereas now the same circles but the solid circles are of our interest. So when these are fabricated on the same line for same dimension of the structure, 4 times they are fabricated, and the average is taken, and then the error is calculated. You can see, as because of the shrinkage, now the percentage distortion is on the negative side, and the percentage distortion, the values are different. So it is very important what is the orientation of the fabrication. Is either you want to fabricate circles or the whole solid part. So your distortion, percentage distortion will be different. Then the same dimension, but the structure of the square are fabricated. So we can see like there are the R1 to R7. These squares are formed. R1 is corresponding to 500 micron square dimension circle, and the R7 is a 50 micron dimension circles. Sorry, squares. So these are the squares, and the dimensions of this CAD model are similar to the dimensions of the circles, but these are the square holes now. The dimensions are the same, principal dimensions are the same, and then they are fabricated 4 times, and the average is taken, and then percentage error is, or the distortion is recorded. Okay, so we can see like similar to the circles, we get the maximum error when the dimensions are on the lower side. So the care has to be taken on the shrinkage of this particular structures, or the care has to be taken on the on the, or the control has to be done on the photopolymerization process to reduce this percentage distortion. Similar, like the similar square types of circles, square type of the structures are fabricated for the same dimensions as that of the circles, but these are the solid squares now here. In previous case, they were hollow. Now here they are solid, and the percentage distortions are recorded over here. So it's quite interesting. Again, when you are going on the lower side, then the distortion is percentage distortion is more. So it signifies that we have to give a plenty of like thought onto the photopolymerization process. So after so much of like this characterization, like 2D characterization, then the entire 3D structures are fabricated. So we can see here, these are some of the 3D structures which are fabricated or the outcome of the machine which we have developed in the Suman Masruwala Advanced Microengineering Laboratory, and they are published in the ASME journal JMPT. So these are the microcones. We can see these are the 4 microcones, and these 4 microcones are having the base of 4 in the CAD model. The base is of 450 micron, and the height is around 425 micron, but we have obtained height of 423 micron and obtained base is of 448 micron. So these are they are like, and we can see the staircasing effect is quite observed here, because we are developing this component layer by layer way. As we are developing the component in layer by layer way, the staircasing effect is quite observed in all these 4 microcone structures. Then this is a micro pyramid. This base of the micro pyramid is 996 micron obtained, and in CAD model it was 1000 micron. Top land of the pyramid, this top land of the pyramid is 274 micron. In CAD model, it was 275 micron. 1 micron is the error that is introduced here. And then this is the micro channel. This micro channel, you can see like this micro channel is fabricated to demonstrate that this machine can develop large range components of the smaller feature size. Large range but small feature size. So this is a large range, that the channel itself is 4 mm by 4 mm itself, like obtained dimensions are 3993 micron by 3989 micron. In CAD model is 4 by 4 mm by 4 mm. And the channel dimensions, you can see that there are the channels here. This is used in some biomedical application, these channels. And these channel dimensions are 146 micron, and this width of this channel is 146 micron. The target in CAD model was 150 micron, and these reservoirs are there. These reservoirs are the counter holes, and these reservoir counter holes are 740 micron and 415 microns. Okay, so this structure demonstrates that the machine can develop the large size component with a minimum feature size. And then last component over here, this shows the large range and the high aspect ratio structure that can be fabricated. We can see this is the tank in tank structure. The outermost tank is of low aspect ratio, but it demonstrates the large range can be fabricated. And innermost tank is of smaller size but a high in the height. So it demonstrates that the high height can be, a large height can be fabricated. So there is no limitation. You can build the component of whatever the height. Okay. So this large component illustrates that the machine can fabricate large range component but have high aspect ratio. Okay, so these are some of the successfully fabricated structure using this MSL. So this is the first part of my presentation, and now I will be taking over to you through the bulk lithography. But what is the problem statement from this MSL? So no problem. The MSL is like very good and promising structures are developed. But what are the limitations of the structure? Like one limitation mentioned here, the stair stepping effect is build direction is inevitable. So we can see like the stair stepping effect is quite observed here in in this particular three-dimensional structure. Wherever the lateral surface is slant, the slant or the slopy, there this staircasing effect is quite well seen. Okay, wherever there are straight edges, like in this structure of micro channel or in micro tank, this staircasing effect is not very well seen. But in first two structure where the lateral surfaces are slopy, we can clearly see the stair stepping effect in the build direction. And this multiple layer, so we are developing in multiple layer by layer way, and in line by line way we are developing 2D structure, and one by one we're developing the 2D structure, stacking it, and they're getting developed the 3D structure. So this multiple layer processing leads to longer build time. So the time required to build this 3D structure is very long. So these are the two limitations, and with this two limitation, it has given a birth to the next process, which is nothing but the bulk lithography. So there are like plenty of methods given in a literature where we can reduce the staircasing effect. Like you can control over the process parameter like speed, etc. At the ends, and thus control the cure depth, and this staircasing effect can be minimized. So this is given by the David et al. In his one of the paper. And one more very interesting paper found by the Pan et al. Like where they have processed this component in a very different way, so that the staircasing effect can be minimized. So if we want to develop, let us say, component with some curve edges at the end, but when we are developing by layer edges, layer by layer way, then we get like this in the component in this particular fashion. So what he has developed is he has after each layer of fabrication, he has taken the component outside the resin, and after taking the component outside the resin, he has designed this particular laser. He has given the laser exposure to over the entire surface, and when he has taken this component outside this particular resin, the meniscus are formed, and this meniscus formation is controlled in such a way that it conforms to the shape of the lateral surface of the component. It conforms to the lateral surface of the component. Okay, and this way, when he is taken out from the resin, it conforms to the lateral surface of the lateral surface of the component, and the laser is shine, and it gets cured, and thus this staircasing effect can be minimized. So this is a very novel approach he has demonstrated in the one of the ASME paper, I think from Journal of Micro Nano Manufacturing. And one research group from the Georgia, David, they have given this single energy exposure lithography. So they have taken one transparent window here or transparent structure, and then it is the laser beam laser is focused entirely in one go, and then the entire structure is fabricated at the bottom of the structure, and then it is selectively controlled at every point. The exposure is selectively controlled at every point by the this DMD, and then we can form the freeform structure below this particular transparent substrate. So this is what actually he has developed, and he has called it as the exposure control lithography. But this in this particular process, he has mentioned that the exposure at pixel on the resin surface of the resin is general function of multiple rays reaching this pixel, and this inverse problem, that is the finding the exposure control parameter for the desired cure depth, is very difficult. So this has given a birth of the bulk lithography. So we'll see at the bulk lithography what is the central theme. So what is the central theme, and then we'll see the process characterization, that is cure depth, width, surface, then the process physics driven modeling of the bulk lithography, and then few of the components which are developed by the bulk lithography. Let us look at the bulk lithography. So for the ease to understand like the difference between the microstereolithography, that is MSL, and bulk lithography, that is BL, I have taken same CAD model which I have demonstrated in the bulk in the MSL process. The same CAD model means same cone type of CAD model is shown over here. We can see in a bulk lithography process, the same CAD model is sliced in a different way. Different way is sliced in this way, and the slice plane obtained are the paraboloids now here. So these are the parabolites. So this is a one slicing plane, this is another slicing plane, and this way the slice planes is slicing this own type of structure or the CAD model developed, which we have to fabricate. And these are the slice planes which are obtained here, which are nothing but parabolites. So the slicing planes are nothing but the XZ planes basically. So these are the XZ planes, and then XZ planes, these cutting XZ planes give the number of parabolites. Now, how we can fabricate this entire this 3D structure using bulk lithography is shown over here. So we are having the argonine laser and then acoustic optical modulator, that is optical switch. So optical switch here, as mentioned in the MSL, is having function to make laser on and off. Okay, but in case of a bulk lithography, beyond making laser on and off, here the AOM is having the function to control the laser intensity. So why it is? Let us discuss that. So in MSL, the function of the AOM or optical switch is just to make the laser on and off, but AOM in bulk lithography is having function to control the intensity as well. So why it is so? So let us discuss that. Now we are having the laser beam coming from the laser source, passed to the AOM, and passed to the it is passed to the mirrors which are arranged on XY scanner, and this XY scanner is flexural based, which is used in case of the MSL system as well. And then from the mirror, the laser beam is focused onto the resin surface using focusing beam. Now here, look at this. Here we have the resin surface, but resin, this is in a build, this is a tank, and on in a tank we are having a resin, and on the top of the resin we are having a glass substrate. So this is the glass substrate, and the laser is focused at the interface of the glass and the resin. So this is the glass substrate and this is the resin, and the focus beam is at the interface of the focus point is at the interface of the resin and the glass substrate. Okay, so what happens now? And the entire component is developed below this glass substrate. Now, what we are doing when the laser beam is scanned? So when it is scanned, let us say for the first parabolite to develop. So this blue, when you have to develop this first parabolite, this first blue section, then when laser beam is scanned for this first parabolite to develop, now the depth required at point to point is different. Whereas in MSL, the depth required from point to point is same. Layer thickness is constant. Now here, what we are doing is entire paraboloid we are going to form in one single line scan, and the depth of the cure depth required for this paraboloid to form is different from point to point. So what is to be done is to get this, the energy need to be varied, because for more depth more energy is required. Okay, so this is the basic fundamentals from what we know. So more depth, more energy is required, and accordingly the energy need to be varied while scanning. So that's why I told the AOM is having very important function in bulk lithography, is not only to make laser on and off, but also to vary the intensity profile or the energy while scanning the laser beam. So while scanning the laser beam, it gives this energy distribution as well, and thus we can get the first paraboloid form. For second line scan, the second paraboloid form, and so and so for by one 2D scan, we can get the entire 3D structure fabricated underneath this glass substrate. Whereas in case of MSL, in one 2D scan, we are going to get only one 2D structure. Whereas in bulk lithography, in one 2D scan, we are going to get entire 3D structure getting developed underneath this under this glass substrate, and that's why this process is called as a bulk lithography. We can fabricate the entire 3D microstructure in one 2D scan of the laser beam, and that's why this name has come, and it is called as a bulk lithography. And so for this is the concept, but to realize the concept again, these need to be characterized thoroughly. So this process is characterized thoroughly by putting the large the scanning the laser beam for variation large variation in the energy, and the cure depth is obtained, and then it is seen that the when the energy is increased, the cure depth is increased, but then after certain energy, the cure depth gets saturated, and the we do not get the further more the curing that is going to take that is not going to take place after certain energy, and there is a saturation of the cure depth. So we can see like some of the trial structures which are formed using this using this bulk lithography, where we can see the saturation of the cure depth that is obtained after certain energy. So this particular animation shows like how this scanning system is different than that of the MSL. So we are having the M1 M2 and the focusing lens all together, and M1 and focusing lens move together, but while moving together you can see like energy is varied by using AOM, and when energy is varied by the AOM, we can get the Q depth variation during the process, and because of that Q depth variation, we are getting the free form structure obtained underneath the transparent substrate. Underneath the transparent substrate, we need to have the transparent substrate here. So this is a glass substrate. The transparent substrate is very much needed here. So the light is passed to the transparent substrate, and it is a focused at the interface between the resin and the transparent substrate, and then the energy is varied while scanning the laser beam over at this interface, and that energy is varied according to the need of the cure depth at of the microstructure, and thus the entire structure is fabricated in one 2D scan of the laser beam. Unlike MSL, where in one 2D scan we are getting the one layer, one 2D structure developed, and layer by layer way we are getting the entire 3D structure getting developed. But here in one 2D scan we are going to get the entire 3D structure developed. So this is the difference between the bulk lithography system and the microstereolithography. So as I said, the process needs to be characterized to a large extent, to greater extent, to see what is the effect of the energy on cure depth, then the width, and also on the surface roughness. Because there's a lot of like issues that are coming into the picture when we are polymerizing this process in this particular way. So let us look at that. So this is the photographic view of the bulk lithography setup. So similar to the MSL, we are having the argon ion laser, then the AOM, this is the AOM, then these are the mirrors, this is the laser path, and then mirrors M1, M2 mounted under the flexural mechanism. Then this is the focusing lens, and this is the focusing lens. This particular part is magnified and shown over here. So this is the focusing lens here, and this is the transparent substrate. That is a glass, and then the glass is placed over this resin surface. So this is the glass substrate. This is placed over the resin surface, and when the focus, this light is passed through this transparent substrate, that is a glass substrate, then its path do change, and so you need to have adjustment in the focusing point again, and that can be taken care by the Snell's law. So the Snell's law can be applied, and we can correct this focus point, and we can redefine the focus point. Okay, now in experimental characterization, this process is characterized for large power range, like in the range of the 10 microwatts to 150 microwatt in the step of 10 microwatts, and exposure time to zero point 0.1 to 2 seconds in a step of 0.1 zero point 0.1 seconds. And the various resins which are used in the characterization are the hexanediol diacrylate, that is HDDA, and monomer. Another monomer was also used, trimethylopropane triacrylate, that is TMPTA, and in which the B benzoyl ethyl ether, this is the photoinitiator, which is activated for the photopolymerization process in the range of 351 to 375 nanometer range. So these solutions are generally used, and the major responses are the cure depth and the cure width for the wide range of energy exposure onto the resin surface. So this particular laser beam is focused at the interface of the glass and the resin surface, and we can find out based on this energy exposure and power, based on this power and energy exposure, this combination means for different energy, I can say for power and exposure time, if you do that, then we'll get the energy, and for this different energy we get this different microvoxel forms, and these microvoxels are then observed under the microscope, but for there is a like tedious process of post processing this when we are taking out this microvoxel out of this system over here. So a lot of like resin is all around that particular voxel, so that has to be taken, that has to be removed first of all. So that has to be removed by the like we have invented the process of like where the tissue paper are placed around it, and it soaks the uncured resin, and then further the acetone solution can be dropped, and it can drag away this uncured resin, and we get freestanding microvoxels form, and then they are observed under the microscope. And when they are observed under the microscope, their width and the height is noted. Okay, so we can see like some of the these voxels, their dimensions, the length and the width, they are noted, and these are the ACM pictures of this micro voxel array obtained by this bulk photopolymerization, and these sizes of this micro voxels are noted. We can see here an ACM. This is a 20 micron size over here, and I mean these are the quite like in comparison to that micron size. This one of the micro voxel picture mentioned here in this ACM image. So all these dimensions are noted for the different energy exposure. Different energy exposure means time and power. So for different energy or time or power or time or the intensity. Okay, so with that we can get that for different energy, these dimensions are obtained like pure depth and pure width, and then they are further these. These are presented in terms of some characterization. So we know that this I'll just quickly cover because this will be very difficult to cover in a very short time. So uh, this laser beam which we are using is having the Gaussian intensity profile. So this is the Gaussian intensity profile that we are having, and this laser is falls onto the resin surface, and the resin surface is a photopolymer, so which absorbs the light, and that is given by the Beer-Lambert's law. That the absorption is given by the Beer-Lambert's law. So this is the Beer-Lambert's law. So working with these two equation, we can get the cure depth and the cured width. This model. So this model, this cured width model, this is called as the Beer-Lambert's cured depth model. Is very widely used, and we can see that in this equation we are having CD, this cure depth. So this cure depth is equal to dp log of Emax divided by EC, where dp is the penetration depth of the resin. So this is the property of the resin. EC is the critical energy of the resin. So this is also property of the resin. So we are having the resin like SDDA and the benzoyl ethyl ether solution. So for that combination, we are having some definite dp value and the EC value, and the process parameter like where our exposure time and the intensity, based on that we can have the Emax. So Emax is the process parameter, dp and EC, these are the properties of the resin. The dp is the penetration depth and EC is the cured energy. So we can see like this is a Beer-Lambert's cure depth model, and it is widely used in the characterization process, and successfully they are used by many researchers in the fabrication of this micro components in using MSL, etc. So if you present now this model in pure depth in dimensionless way, then we can take this dp on the left hand side, and thus we can get one dimensionless parameter called dimensionless depth, that is CD divided by dp, and log of Emax divided by EC can be called as dimensionless energy because it is a ratio of energy. So we can call it as a dimensionless energy. So log of Emax divided by EC is dimensionless energy, and CD divided by dp is dimensionless Q depth. So if you make the analysis in dimensionless fashion, then this analysis can be useful for any combination of the reagent. Okay, so this characterization is presented in this dimensionless way. The CD there by CD over dp, CD there by dp against the log of Emax over AC. Now, if we see this Q depth Beer-Lambert's law, this model of Beer-Lambert's law for Q depth, then CD divided by dp is equal to log of Emax over AC. So on a graph of CD divided by dp against log of Emax over AC, it should be a 45-degree line, a straight line with a slope equal to 1. So this is a straight line with slope equal to 1. So this is the Beer-Lambert's model, and we can see our results when we do the characterization for large energy exposure. For low energy band, it quite well matches with the Beer-Lambert's model, but when we expose to high energy dose, then we get deviation from the Beer-Lambert's model. So there is a regime 2, it deviates slow transition from the Beer-Lambert's model, and regime 3, it shows the saturation of the cure depth, and whatever the energy we are putting after certain point, the cure depth do not get changes. So this is what the characterization that we get for the wide range of energy exposure. Further, if we introspect this on the time scale, that for the different time as the energy is put by the different time exposure, intensity and time, these are the two parameters which gives the energy. Okay, so energy can be controlled by time or intensity, right? So these are the two very important parameters. So for large energy, we can have large exposure and low intensity, or we can have large intensity and lesser exposure. So that can be possible. So if we introspect from that point of view, then and plot all that cure depth curves, then we can get the different such curves for the different times. So here the various times show here 0.3, 0.6, 1.3, and 2 seconds for these different times. These cure depth characteristics are plotted. Now the very interesting point that is observed in this particular characterization is that for a constant energy, for constant dimensionless energy, like this is the dimensionless energy axis, and a constant this vertical line shows the constant energy line. So on constant energy line, we get the different cure depths for same constant energy. So this is the constant energy line, and these are the point of intersection on the various time curves. On various time curves, it shows then on the y-axis that different cure depths can be obtained for the constant energy. So this is the interesting physics that is the observed using when we characterize this bulk lithography process. The one has to understand what is the reason. The reason is that when we look at the point A and point D, the point A is on the time of 0.3 second, cure depth line for 0.3 second, and point D is for the cure depth for the 2-second exposure. So when 2-second exposure means intensity is very small, and point A means the exposure is time is small, exposure time is small, and the intensity is very large. So what happens when intensity is large and the exposure time is less? The less exposure times do not give the sufficient time for the photoinitiator species which are present in the resin to come to the reaction zone and the form a reaction. Okay, so that is what actually is happening, and to absorb the photons. Okay, so this time for absorbing the photon is less, and that's why the laser light is able to penetrate to large distance, and thus large large depth is possible when the exposure time is less. And when the exposure time is more, the photoinitiator gets the sufficient time to diffuse to the area of the reaction, and it absorbs the photons more, and thus the light is not able to penetrate to a large distance. So this is what actually we propose this physics in a process, and then the experimental characterization, experimental model also is process. I will skip through this. And similar line on similar things, we have investigated the surface toughness also, and we have optimized for the surface toughness case. And now this little bit about the uh, this, what is the this animation perhaps will be interesting to see. Now, what is happening in the bulk lithography? So when we are putting the laser light at the interface of the glass and the resin surface, resin consists of the different species like photoinitiator and dissolved oxygen. So this dissolved oxygen first of all react, and then photoinitiator react. The dissolved oxygen reacts, and that is in micro nanoseconds, so that can be ignored. Okay, and then photoinitiator comes, and that is of our interest. So photoinitiator comes at the reaction zone, and it absorbs the photons, and the photopolymerization get triggered, and we get the voxel getting formed. Okay, which I've shown the optical images of the some of the voxel, and the laser light try to penetrate to the large distance, and at the same time the photoinitiator is diffusing. Okay, so this is showing is shown in this animation. So I'll run that animation and just look at that. So first of all, the dissolved oxygen gets reacted, then diffusion of photoinitiator at reaction zone, and it leads to formation of the voxel. Now this voxel acts as a lens with a refractive index gradient, and thus it acts as a lens, and for further next process, for next penetration, there this acts as a lens, and thus we get a focusing effect within this resin. So I can show that the lens-like effect due to refractive index variation, and we get focus area and then defocus area, again focus area and defocus area, and so and so. And later on, after some time, there is the light trapping phenomena, and light do not get penetrate to a large distance. It gets saturated over here. Rather, we get, because of the scattering, the cured voxel get elongated in the lateral direction. So like this. So this is how we get the profile of the voxel with respect to the uh, higher energy and higher time. And this is what actually the physics given here along with the chemistry what is happening. I will skip through this, and this is the like governing equation for the which is used in this on this simulation. So we are having nonlinear Schrodinger equation that is basically based on the wave equation, and along with that we have coupled with the diffusion of this photoinitial species, and then that model is presented, and with this data we can see that for the different intensity profile we get the different pattern of the propagation. So this is for the low intensity beam. When it is a focus at the interface, then we get this propagation pattern. When we increase the intensity, then we get the photopolymerization voxel getting formed. At low intensity, photopolymerization do not take place, so it proceed in this way. But when the intensity is increased, then the we get the photopolymerized voxel form that acts as a lens, and thus we get focusing effect within the resin, again defocusing defocusing region, and so it get proceeded. And when the intensity is much high, then this gets like leads to the scattering of the light, and we get such a pattern over here. So this is had the medium intensity and shown over here, and this is again already I have covered. I'll skip this. This is for scattering, and we can see here the experimental result and the simulation results, how they quite well matched. So these are the experimentally observed the one voxel from the bulk lithography, and how precisely it is captured using the simulation, and then that compared over here shown in this plot over here. So maximum deviation is 7%, in variation in depth is noted here. And then these are employed in the fabrication of the various structures using bulk lithography. I can show that some of the structures here. What is the assumption in this model is the diffusion of oxygen is not accounted. So those who want to further study maybe in a scale of nanoseconds or maybe lesser than that, they can go ahead with this particular consideration of oxygen diffusion. Then prediction of pure oxygen is based on energy threshold model, but there are like so many things like scattering and all which is not considered. So people can use that. Thermal effect on mobility of species is not considered. So these are some of the assumptions. So based on that, those who are want to work in nanosecond or lesser than that time. So these are some of the points that can be explored further. Now I can show some of this is the process plan. So based on the characterization, the one can go with this process plan to fabricate the structure using bulk lithography. So one has to develop a 3D CAD model, and then the exposure time he has to fix first of all, because bulk lithography, the characterization as we see that it is highly dependent on the exposure time. So intensity and time, this leads to the exposure energy, and thus it is very highly, as it is highly dependent on exposure time. So exposure time is a input parameter. This leads to the times in the speeds of scanning of the laser beam, and also this leads to the pointing the maximum energy distribution log of Emax over AC, and along with the CD over DP we can determine the scan pitch distance. Okay, and then 3D CAD model using this scan pitch distance we can be used to generate the depth contour data, and then it can be implemented for the energy variation data, and that energy variation data can be given to AOM, and thus we can definitely fabricate the component using bulk lithography. So this is the process plan, which is fairly complicated than that of the MSL process for the bulk lithography, but when we implement that, we can see that various structures that are very good structures which are fabricated using bulk lithography. So as I mentioned, in bulk lithography process, we can fabricate a component in one single 2D scan of a laser beam. If the same, this is a one sinusoidal type of a like structure, which is the one lens kind of a structure, and these are fabricated using bulk lithography. You can see if this structure is fabricated using the MSL, then we would have got the number of layer by layer or the staircasing effect on the lateral surface, but that is not seen in case of a bulk lithography. We cannot see like staircasing effect in the bulk lithography process. But however, we can see this structure is found in a regime 1 in the characterization. If we go beyond certain energy and in regime 3 or regime 2 and 3, then we get the similar structure like this structure, but very rough in nature. So one has to avoid the regime 2 or regime 3 if the target is to fabricate the smooth free form surface using the bulk lithography. Then these are the Fresnel lens, which is fabricated using the bulk lithography, a circular section with the variation in the cure depth. So this is fabricated. And then this is a micro cantilever, which is fabricated in single go using the bulk lithography process. So these are some of the process characterization and the photopolymerization modeling, which is covered in this bulk lithography. I leave it to you. I will leave this presentation to you, and this last slide where the bulk lithography is falling among the various micro machining processes. So that is shown here. So this bulk lithography is having the range. You can fabricate something around 20 micron to 1 mm, and it can fabricate the 3D complex shape structure. So this is the region of the workable region for the bulk lithography, and compared with all other different MEMS based processes, just for the knowledge. And these are the possible avenues. So those who want to further explore this bulk lithography to a greater extent, they can try over this, and they can contact with me for further assistance required in that direction. So bulk lithography of ceramic and metal is not yet tried. We have tried it for the photopolymer resin, but we can have the mixture of the ceramic nanopowder or metal nanopowder, and we can make a slurry, and we can get the component of ceramic and metal, and we can sinter it, and then we can get the 3D component of the ceramic and metal. That this is a possible avenue. then cured voxel with tunable properties. So we can tune the properties using the different proportion of the photo initiator, even with the different loading of the ceramic and metal, that can be possible. So, or we can change the focus lens or defocus it, and we can see like what is the voxel form and their properties, or we can based on that we can have refractive index gradient. So this pure voxel with tunable properties also can be explored to a greater extent. Then use of non-Gaussian beams. So we have used so far non-Gaussian beams. We can use different profiles of the beams, and you can explore these different shapes of the laser beam and its effect on the photopolymerization. Then consideration of diffusion of dissolved oxygen in first principle modeling, that already I talked with. Then statistical design of experiment to study the effect of following parameters on depth and width can be considered, like ratio of monomer and photoinitiator mixture, then concentration of UV observer, then defocus laser beam and resin substrate interface, etc. So this can be possible. So there are different avenues or future scope which is available. So with this, I stop here. But last very important slide. This is possible with with the team effort, and I thank my supervisors, and also I thank my team members when I worked in the Suman Mastawala Advanced Microengineering Laboratory. My MTech students also, they helped a lot in the characterization, in developing the setup, and so and so. So I thank all of them. I thank my family member, and this is the laboratory where I work. So this is the picture of the same. These are like the different setups developed indigenously in that laboratory. One can visit by taking permission from Professor P.S. Gandhi and Professor T. Kundu, and they can see all this particular setup over there. So I thank all these things, and then I thank all the participants of this program for patience listening to me, and for any queries they can contact me. I have given in my email address over here. So this is my email address, and this is my telephone, my mobile number. So you can contact me on mobile or the email for further any discussion if you needed in this particular line. So I thank you again, organizing team of the VJTI. And special thanks to Dr. Dattaji Shinde for giving me opportunity to discuss this topic to you in this particular workshop. Thanks to Professor Attar as well, and all the team member of this particular Atal workshop. I thank the AICT Atal scheme, which has made it possible for all of you to attend this workshop, and for me also to give this particular the presentation in front of you. So I can take few questions if there are. Thank you very much.
Thank you, sir. Thank you, Bhole, sir, for a nice presentation and on the technical topic. I request to the all participants, please, if you are having any questions, you can able to unmute yourself and you can ask, or either you may write down on the chat box. Please, request to all participants. Anyone who wants to ask something?
Yes, questions are welcome.
If you are having any problem issue with the mic, you can able to write in the chat box as well.
Sir,
Yes, you can.
sir, I want just information about pulse echo detector, sir.
What is that?
Pulse echo detector in medical uses are there, na sir?
Yeah. That is that can be. I mean that I have not worked exactly in that line, but people have that MEMS in MEMS area in that in domain. The people have used some kind of a actuation like piezo and the smart memory alloys, and they have developed it on the cantilever structure and developed that particular kind of a sensor.
Okay, sir.
Perhaps I can give like one of like you can search the papers from the Dr. Rao, who is the director of IIT Delhi.
Okay.
He has worked more in this area. Yeah, he has worked more in this area. And there is one like NanoSnip, one startup under his guidance that has started. Dr. Nitin Kale is the CEO of that particular. So they have developed so many instruments using such for such biomedical application.
Yeah.
So definitely I can share that with you if you can write the mail to me, and their email ID and telephone number. Dr. Nitin Kale is very helpful. So he definitely can help you in that direction.
Okay, sir. Thank you, sir. Thank you, sir. Okay, thank you, sir.
Yeah. Any other member,
Yeah.
participant wants to ask something?
Sir, my question is, in micro channel,
Yeah.
we using XY lithography, can we add
Yeah.
some drafts in channels? So
Draft of what nature? Or can you give the geometry type, like explain that?
if trapezoidal, I want
See,
to
there
do
are in
trapezoidal
in
channel.
MSL we can do that trapezoidal. No problem. We can do that trapezoidal. Absolutely, we can do that. There are like the various structures I have not shown here, but there are many more such trapezoidal structures which we have developed in our laboratory. And in micro channels also we definitely can do. If you are getting some advantage because of the geometry, you can very well process. And now this version is whatever I have presented, like the is the old system. Now the laboratory has come up with many more advanced feature into it, and definitely that can process whatever the geometry you want, like trapezoidal feature, etc. That is very much we can do possible, no problem.
Yeah. Bhole sir, can you able to see the
Even
chart?
in using bulk lithography also we can do that. Okay, both processes, using MSL and using bulk lithography, both with both of this process we can do that.
Sir, one more question was that for a particular one layer in bulk lithography, how much energy or
Yeah.
intensity is required for one layer?
For one layer, it is something in power way. I can tell you, in for saturation to happen, it is up to 150 microwatt. So whatever after 150 microwatt you are giving, your depth is not going to increase. Okay, that almost come to the saturation level, and for that saturation level, the 150 microwatt is sufficient.
Okay, sir. Thank you.
Okay. Bhole sir, can you able to see the chat box? Some question is there over here.
I can refer to chat box. I think actually I'm new to this.
Okay, sir, I
I'm
will
not
read.
used to.
I will read.
Yeah.
Manju Hassan has written this is, sir, effect of sintering in the lithography.
Effect of centering.
Sintering.
Yes,
Yeah.
sintering. Ajay, effect of sintering. Sintering is the another process. It is I mean, we can do ceramic and metal powder. We can mix it into the resin, and then we can form a green component, and that green component we can sinter later on. So sintering is a different process. Sintering is not part of the bulk lithography. We have done to some extent this particular this trial experiment, and we have got good successful result on this using this bulk lithography and processed by the sintering for the ceramic metal powder, that is alumina and all. And Dr. Chandrasekhar is there, whose paper you can refer from the IIT Bombay, who has published from our extending to this bulk lithography for the ceramic and metal bulk lithography. So sintering is the allied process or post processing process, is not directly connected with the bulk lithography. Bulk lithography is not integrated with it, but using bulk lithography we can have the green component, fabrication of green component. Okay.
Any other questions from the audience, please? I hope there is no question from the participants. Already they have been asked the adequate questions. So once again, the thank you to Professor Bhole sir. You have been very well in depth of MSL as well as the bulk lithography. You have been given the highlights about it and in depth knowledge about it. You have been explained very well about the experimentation work as well as the some analysis work as well. So thank you, sir. Definitely the participant will get some from these sessions, and definitely they will be try to implement and try to get it knowledge and in depth the research work, or maybe they will be doing some motivation from this work and they will do something. Okay, thank you, sir, once again on behalf of VZTI from the production department.
Thank you very much.
Yeah.
Thank you, sir. Thank you to all of you. Thank you to all the participants. And my email address and my mobile number are already shared. I have shared the PDF version of this PPT presentation with the Dr. Dattaji Shinde sir also, and that can be shared with all the participants. And any questions are there, they are free to call me or write a mail to me. I will be happy to answer all those. Thank you, sir. Thank you very much.
Yeah, thank you, sir. Thank you. And dear all participants, this session number 2 of the day 2 has been finished. And for the one important announcement for the session number 3, we are having the session number 3, and that will be going to start by the 4 p.m. Please, it is by the Dr. Mote sir. Once again, please remember that one. The session number 3 will be going to start by the 4 p.m. by the Dr. Mote sir, IIT Bombay. Please take a note of it. Okay, and in this way, session 2 is done, and we can once again meet by the 4 p.m. sharp. Thank you. Thank you, Bhole sir. We can
Yeah, thank you. Yeah.
Okay.
Thank you, sir.
We
Thank
have
you.
to join with the same link. Huh?
Yeah.
Same link.
Pardon me.
Same link. We have to join with the same link.
Yeah,
Sir,
same
or-
link is there for the attendance as well as feedback. Please take the same link. Whatever it is mentioned.
Okay, okay, sir. Thank you.
You have to just select the
Yes,
drop-down menu, select proper session, and you can mark your attendance as well as give the feedback. Please.
yes, sir. Thank you, sir.
Yeah. Okay. Do you require once again? I will mention over in the chat box if you want.
No, sir. We have no problem.
Then also some people may are having some problems, so I will be going to mention.
Okay, sir.
Wait for a second. Just I'm going to. Yeah. Okay. This is
देख देख सोफा वो गिरे ना नीचे
Sir, we could not see your screen in the sharing mode. Could you please check it?
So my screen is not visible. Okay, so
I think it is again.
just
disabled.
give me a minute.
Yeah, please go ahead.
How about it now? Can you see?
Yeah, it has been shared, sir. So put in the presentation mode.
Okay, so I hope this is now in a full screen and
Yeah, it's full screen, sir. So you may start.
okay, so good evening and thank you, Dr. Shinde, and sorry for some hiccups in sharing the presentation and so on. So for next 1 or 2 hours, I'll be talking about essentially the micro or the nano fabrication. And typically I'll touch upon the domain of high energy particle based means to get into the micro and nano fabrications, and particularly I'll touch upon the electron beam or e-beam methods with which we achieve this fabrication. So as Dr. Shinde introduced, I'm from Department of Mechanical Engineering, typically working in a manufacturing group, and my specialization is in the micro machining, ultra precision machining, micro nano fabrication, and so on. Okay, so before getting into the e-beam lithography and particle-based nanofabrication, high-energy particle-based nanofabrication, that's what usually we call it. So before getting into the nanofabrications, we need to understand some basic concepts of a microfabrication. Okay, so we'll try to differentiate it from the micro machining. So we are talking about the microfabrications that essentially goes into the sensor fabrications, integrated circuits, and so on. And of course, some of the devices, MEMS devices that actually combine the essence of both mechanical devices as well as the electrical or the electronic devices. So if you look at a typical microfabrication process, so in that sense, I hope you can see my pointer. So in that sense, if you just look at the process, most of the devices, what we know, they are the silicon based. Okay, so the idea is you get a silicon wafer. Of course, we have the different material choice too, but that is not important at the moment as far as the microfabrication is concerned, because that will be decided by the final application. But what we need to know is about the way we are going to have this interesting structures, interesting patterns that we want to put it on those domains. Okay, so typically it goes like this. We will start with the complete wafer. Then whatever the pattern we want to produce, so they will be in the form of a mask. Mask is basically a replica of the kind of a structure we want to transfer it to the final material. And through the optical projection system, so we're going to have this particular pattern projected on the wafer size, right? So while doing so, we must understand here, I'll also touch upon in later stages, this is not a direct writing process, okay? The structures will not be directly created, okay? Because essentially the kind of exposure what we have is not that high power, and in fact, the phenomena what we use in order to fabricate the structures is a bit different. So just like what we see in case of our conventional manufacturing processes, the like just like if you just compare it with the CNC milling process or even the laser writing process, okay, so wherein we create the structure directly, but here we're not going to write it in a direct manner, but we have certain intermediate material called as a resist, over which we are going to first of all pattern it, and from the resist we are going to have this structure transferred to the, let's say, at the wafer level and so on. And then, since this is at the small domain, so multiple structures will be having over the entire wafer, then we slice the wafer, and what we get is a die or an individual unit, and that individual unit will go into the application. So that could be a your integrated circuit, that could be a accelerometer, that could be a sensor that goes into various industries and so on. So it starts with the wafer for material, then we'll be having a multiple material addition process like a deposition process. Then we have this optical projection and lithography process, and that's how the process goes. So the idea of the lithography is quite old. Okay, so I'm just using the word lithography. Okay, I didn't say anything else. So lithography, the litho basically is about the stone, and the graphy is kind of a writing. So if you just look at this particular slide, you will notice these are the cave paintings, so which were almost 40,000 plus year old. Okay, so therein you can see a nice hand is being impressed. Okay, so this is pretty old. It's a prehistoric times. So in that sense, if you just look around, the way the hand is impressed upon, and this is what precisely we do as a kid when we actually try to make use our hand as a pencil, and we put it on a paper and try to carve it out. So what we are essentially doing is that we are using our hand as a replica or a stencil, and that we are going to transfer, let's say, on the paper, or in this case, they might have done simply put their hand over the wall, and they might have some primitive colors. They might have splashed it over the hand, so with which the hand impression was sought. Okay, so this is a very crude idea of how you are going to make use of the stencils or the patterns, and in order to generate a final print. And this is very similar to what we do in some other applications that also we are well aware of, if you just consider a case of screen printing. So in that sense, again, we are going to have certain patterns, and those patterns basically we transfer via some means onto the final target material. Now we'll talk about the next level. That is, we just talk about the lithography. The next is the optical lithography. So this is the essence of IC manufacturing. Okay, so wherein the process is similar. Now, instead of stencil, what we have is a mask. Okay, so with this mask, we'll be having certain pattern. So this is very simplistic representation. Now, in this case, what we have here is a sort of a pocket that we want to fabricate at the end. Now, this mask will be created with binary tone, in the sense some portion of this mask will be having a transparent region, and rest of the part will be opaque, so that light will not pass through. So immediate implication of this, if you shine a light over this, certain portion they are going to block the light, and rest of the portion they will allow light to pass. Now, as I mentioned earlier, now we want to transfer this pattern. We want to have this pattern finally to be fabricated at the wafer end. So how do we do that? Again, we must remember here, we are not going to directly create a structure on a final material. Okay, so in that case, what we need is some sort of a intermediate material which is responsive to the radiation. The radiation in this case is the optical radiation or the simple light. Now this light, so the material should be responsive to the light. Then in that case, which material actually respond to the light? So we call it as a resist. So this resist basically, they respond to the light. Now, when I say respond to the light, what does that mean? It simply means that whenever such material is selectively exposed to the light, okay, so it actually changes its properties. Now, which properties? The simple property, if we just take the solubility, right? So whenever the exposure is happening, certain pressure, portion which got exposed to the light, either it becomes soluble or insoluble. So again, that will be decided by the tone of that resist. Okay, so if wherever we are exposing the material to the light, that particular portion, if it is getting insoluble, if it is getting soluble, okay, so in that case, we'll call it as a positive resist, because wherever the exposure is happening, it becomes soluble, and subsequently, when it is subjected to the developer solutions, that will get simply dissolved. Exactly opposite happens with the negative tone resist, wherein wherever the exposure happens, if you can see it here, the exposure is happening wherever I am moving the cursor, so that becomes insoluble. Okay, so if I just expose this particular resist to a developer solution, wherever there wasn't any exposure, that much portion will just go wash away. It will be dissolved. So you can see it here with the different tones, we're actually getting close to the desired structures what we want. Okay, so for example, this is the pocket if you want to create. Now, essentially, we create it in a different tone on the photoresist. Still, we haven't made the structure on the final material. Okay, so it will be first of all decided by what kind of a tone we are using. Now the next problem is, how do we get this structure to the final material? So in that case, we need to have a certain solutions, or we call it as etchants, that basically in a position to dissolve the target material or the final material. Now while doing so, now this resist, or rather a photoresist, basically it will protect the material beneath it, because we selectively remove the material on the resist. So if we just now follow the tones, if we are using a positive resist, this much portion actually we have it. Okay, this much portion we have it as a resist, and if you are having the negative tone, this is the resist portion. That means the material beneath is open here, and in the other case, the material is open over here. Now, if I use the next tone, the next step of the etchant, what will happen? Whatever the leftover resist we have, that will act as a mask. Okay, so that will protect the material beneath. So if I just carry out the next cycle, we'll have the structure created. Okay, so it will be created in a negative sense if we are using a negative tone. It will be created in the positive sense if we are using a positive resist. And of course, based on this, we can have a multiple operations possible. Just like if you want to add a material selectively, then again we'll be having this remnant resist that will protect the structure or the material beneath, and you will have a selective deposition. So much selective material removal or the selective material addition will be possible by the tactical use of those resist. Okay, but again, just to recap the steps, the structures first of all will be created at the resist level, and then we'll transfer those structures to the final material. So this involves multiple steps. But the key thing is that whatever the structure we want to create, first it need to be created at the mask level. Okay, so this is kind of a replica we need to have. Then whatever the complexity we want to impart, that will be happening at the mask level. Rest of the process is fairly simple. All right, so the way we expose it, that actually distinguishes the lithography processes. So initial days, it is a simple process. We just had a mask with the desired structure. This is the photoresist and the substrate over here, right? So just to shine a light, we have this binary tone mask wherein either light will pass through the transparent region or it will be blocked by the opaque region based on the features what we created on the mask. And same exposure is going to happen at the resist level. So this was the simplest process, but with the advances in this lithographic projection systems, now we have additional optics placed so that this photo mask or whatever the features that can be reduced. This is very similar to the projector-based cinema theaters. Okay, so wherein the process is quite opposite. I mean, therein the film, or you can take it as equivalent to your mask, is a smaller and it will be projected over the larger screen. Here, what we have, mask with large size, and the optics will enable it to be projected in a smaller domains. Okay, so likewise, on a given wafer, which could be of a few inches in the diameter, so we can have the structures over a few millimeter domains, and if you just look at the feature sizes, they could be of a micron dimensions. Okay, so these are essentially the projection systems. This is a 1:1 projection because we're not going to have the reduction in the sizes like in this system over here. So this is the most popular means used in the industry, but of course it comes with a cost because we have this very complex optics involved in order to have the photomask feature projected over the photoresist or our wafer. And of course, the direct writing is known to us. Typically, the way we make use of the lasers. Okay, so wherein we scan the laser beam point by point over the resist, and we alter the properties. So advantage of this system is that you don't require a mask. Okay, so simply you need to do the point by point scanning by the laser. Okay, so this is just an example that will actually give you an idea by which how the complex process is, although it happens to be very simple over here. But if you notice here, it not just involves the exposures, but it also involves many intermediate steps wherein you keep on adding the material and removing the material and so on. So that's what if you see at this particular structure. So this is not a typical two-dimensional structure. So if you can see your screen, it has a certain overhang portion. The structure is happening at the multiple levels and so on. So for that purpose, we need to have a multiple steps involved, wherein we use the lithography process, what I described here. Okay, so that this step itself will involve around 6 to 7 steps. Okay, so when I say the lithographic, it will involve all those right from the coating of a photoresist to the exposure by the optical system, and then etching it out and the transferring the pattern and so on. But many times the complex structures involves in between process where you keep on adding the material. For instance, in order to arrive at the structures, we create a recess like this, then we deposit the material and we take away the support so that we have a overhanging support. And over this deposited material, then again we have our next lithography cycle. Okay, so we just try to distinguish here. The first lithography cycle is just to create this recess, and over which we deposited the material, and over this deposited material, then we have this particular this cantilever sort of a pattern created. Okay, and then we then simply get rid of this sacrificial layer at the base, and what we have is a overhang cantilever sort of a structure which is connected with the base. Right. So when we say about the lithography, basically there involves around 5 to 6 steps, and likewise we go for many iterations in order to get all the features created over the structures. Okay, so this particular diagram or this particular example we give you the glimpse of optical lithography or photolithography. Now question arises because we're just talking about microfabrication. Okay, so as we know, we have been hearing about the Moore's law for decades. So what it states is that every 1 or 2 years, okay, so the number of transistors that can be accommodated in a given area, they essentially gets doubled. What, in other words, the features that we want to create, okay, so the size of those features, they are getting smaller and smaller. Okay, so there are 2 issues involved. I mean, let's say if you just take example of processors, okay, so in that sense, first of all, you need to have a proper design in place so that the intended functionality will be achieved. Okay, so it's not just that you just keep on reducing the feature size or the dimensions and the thing will work. So it should work in principle, it should work at the design level, and then comes the fabrication challenge, wherein we should have a fabrication process in place that actually can translate your design into reality. Okay, so it's a design challenge as well as is a fabrication challenge. So in that sense, if your design is ready, then what should be the fabrication solutions, right? So you cannot just keep on reducing the dimensions. Okay, so when we want to venture from macro world to the micro world, from micro world to the nano world, okay, so in that case, there are many challenges that are thrown upon. So as far as the microfabrication is concerned, so what are the challenges involved? What actually limits how small we can get with those steps? Because optical lithography is established industry practice. Now the real question is how small we can make. Now when we say small, it's not just smallest dimension we can achieve. That itself is a challenge. How small a particular feature can be made. If you just take example of the memory devices, okay, so the memory device structure is pretty simple. It's just a periodic lines. It's a series of lines. Okay, so just like channels, you are going to have it for the materials. Now, in that sense, the first challenge will be how small that particular channel, that particular line, okay, so that can be met. So that is the first one. But more than that, we can have a method with which we can actually make a very small line, very small trench, or very small channel can be devised. But the problem arises when you have many such lines that are being put together. Okay, so then actually the real problem starts creeping in. So typically, if you look at memory structures, they have a series of lines. And what we're looking at, how densely these lines are packed. All right, so this is very similar to you have a periodic array with a defined spacing. So just like for the screw threads, we have a pitch defined. In the similar manner, we have a pitch defined for these structures. Right, so what we have here is the line created, then we have the space in between, and so on. So line and the space, that in totality will give you the pitch, right? So the creating a line is not a big challenge, but creating a pitch with a desired density, right? So that is essentially a problem, right? So let us try to see now what's the problem and why making dense structure is an issue if we just go with the optical lithography principles. The problem arises mainly because of a very peculiar phenomena with the light exposures. we call it as a diffraction. Okay, so just now imagine two processes. Let's say we have these two openings over here. All right, so just you can imagine a sort of a, you have a series of lines that we want to fabricate. So that can be patterned over the mask. So this is a mask. Now, in initial days, the idea was you just create a mask and place it over the resist. Of course, there will not be any size reduction happening here. So whatever the feature we have it over, they will be easily transferred because of the exposure through this region. Now, what happens if I just keep moving this mask away from the resist? Okay, so am I going to get the same exposure at the resist level? The answer is no. If we are keeping it in a very close proximity or with the contact mode, obviously we can expect the same feature to be exposed with the same dimensions. But as we move it away, what will happen? These edges of these particular features, from those edges, the light will start diffracting. And once the diffraction happens, we know they are no longer collimated as we would have expected. They will just scatter around. So in case of a contact, this possibility is almost nil. But as we just move it away, the diffraction actually start deteriorating the projections. So typically, if you just try to imagine, let's say if we have this opening. Okay, so we have this opening, and this is the resist, this is the wafer. Now this is just, we turn it by 90 degrees. So exposure is along this line. So this is the light exposure. This is the opening. And what we have are wafer and the resist configuration. So ideally, we would expect, let's say this W is the opening size. We want exposure to be happening exactly of the same dimension. That is W. But in practice, due to the diffraction, as the distance between, let's say, from our mask to the resist, this distance starts increasing. We have exposure getting different at this resist level. So just typically from the idealistic perspective, if it is a contact type of exposure, we'll have this binary exposure. That means wherever the opening is, we have the maximum light exposure, and wherever the opening is not, the exposure is nil or the zero. But as we increase the distance, we would see the exposure is something like this. So what does that mean? That means the region where we wanted to have the full exposure, it is not exactly complete exposure. And ideally, we would have wanted almost nil exposure into this opaque region, but we get some unintended exposures into these domains. Okay, so whenever the exposure is happening, what we know, the properties of resist, they are going to be different. So what we expected, this pattern to be developed, but instead we'll be having some development happening around this region. Okay, so this is the simplest way to tell you about how the diffraction spoils the structure fabrication. And this diffraction, actually, we know it becomes more problematic. Okay, so when we actually try to reduce the size. For example, if I just go back here, now this is the W what we target. If I keep on reducing this dimension, okay, so what we see, this is the exposure. So this exposures or this diffraction, it gets worse and worse. Okay, it basically worsen. I mean, that means this gets broader and broader. All right. So smaller the W, we would expect there will be more diffraction. So this is actually what we don't want to have, because as we said, we are looking at reducing the dimensions, but if we keep on reducing the dimension, diffraction is going to spoil the show. So this is quite evident in many practical examples, especially if you are looking at the stars, or even simply you're driving a car. If you're looking at many light sources at a far distance, so what you would notice is that those light sources, if they're quite far apart, they will try to merge into each other, as if there are 2-point sources, you will feel that there are no 2-point sources, but the light is coming from only one source. For example, if you just look at this constellation is quite familiar to you. So in that case, if you just look at what we know, we call this particular constellation as a Big Dipper, or in our sense, it's a Saptarshi. So Saptarshi, the name implies there are 7 stars involved. Okay, so those are, if you just look into the sky, look at the sky, you will easily distinguish those 7 stars. But if you just look at the star over here, we assume it to be 1 star, but in reality, there are 2 stars. But we cannot just distinguish these 2 stars because they are quite far apart. They appear to be point sources. Since they are quite far apart, the diffraction actually makes us to believe that whatever the light we receive from that region, it's coming from a single source. Or in a technical terms, our eyes are not in a position to resolve these 2 stars differently. Now you can take an analogy and look at our mass fabrication. If we are having a very small features, they are closely spaced, and if you just expose the light, okay, so at the resist level, the exposure will not be in a position to distinguish between those 2 features. So these 2 features, simply they will merge together. Okay, so that is a big problem when actually we want to get into the smaller dimensions. And so there is a physics behind it, what phenomena goes on. And there is a criteria defined wherein how small these 2 particular sources could be so that we can resolve them. So what is the limit involved? All right, so this limit, we call it as a Rayleigh limit or the Rayleigh criteria. So typically, if you have just, let's say, if you have one opening on a screen, and if you shine a light, the typical diffraction pattern looks like this. We call this as airy disk. So ideally, we would have expected only this region as a bright, but the diffraction gives you a fringe pattern. Okay, so this is again not intended because we just wanted to have a single spot projection, but instead what we get, the pattern like this. And if you bring one more opening close to this one, these all patterns, they will merge together. And eventually, if they are very closely spaced at the screen level, will not be in a position to distinguish between the 2 sources. Okay, so that's what you can see it here. If this is the just one opening, how the intensity pattern. Okay, so this is the central maxima. So that is what we wanted to have it, but instead what we get is this. And if we have a multiple openings, then we get a multiple patterns like this. Okay, so this is just a typical with the circular hole. Then we can have a similar patterns for other geometries. So you can see it here. If we just keep on moving these sources close to each other, then it will appear that they are getting merged together. So although even we have 2 distinct sources, but at the screen level, unless at the resist level, what we see as a single entity. So we lost the patterns, we lost the sources, or we lost those features. So how these two things we can bring the closer? So there is a criteria wherein we say that the maximum of one source, if it is coinciding with minima of the other, okay, so in that case, that is the limiting case. If we try to push it close to each other, then we are going to lose the structure. Okay, so this is a serious problem as far as we keep on hunting for the smaller feature. So again, I'll go back to this earlier case wherein I said making a single standalone smaller entity is a bit easier, but if we have a multiple small entities closely spaced, okay, or if you have a very dense structure of a variety of the patterns, then simply those patterns, those exposures would merge into each other and we'll lose them. Okay, and the culprit is the diffraction. Now, how to deal with this diffraction? Okay, because still we are talking about the optical lithographies. Our exposure source is a light. Light is basically an electromagnetic radiation. So there are various tricks being played wherein we can actually minimize this diffraction effect. Of course, I'll not get into all those methods with which actually we tackle this issue. But it's very simple to understand. Concept is coming from our, again, basic physics. As we said, the diffraction. Okay, I'll just go back here. So diffraction will be decided by the spacing over here. Obviously, it will be decided by how small feature size we want to have. But apart from all these factors, the diffraction will be decided by exposures, or what is the wavelength of exposure we are using. Right? So if you want to minimize the diffraction, apart from other factors, usually the other factors are not in our control. For example, if I want to make a certain feature size of a dimensions W, okay, so that is the target. So we can't change that dimension. We need to design our fabrication processes that we should be in a position to handle it. So in that case, is the wavelength of the radiation that plays an important role. So what basic physics tells us, if we reduce this wavelength, then the diffraction also reduces. Okay, so that is the clue for us. How do I improve on the resolution? How do I go to the next level of miniaturization? So you play with the lambda. Of course, there are many other optical tricks we can play with, but let us just focus on reducing the wavelength. Okay, so when all this lithography method started, optical lithography, so initial light source was a mercury vapor lamp. Okay, so essentially it's a broadband wherein we have this visible light coming in, and then we can make use of certain filters. So that can give us wavelengths in, let's say you have the red light, you have the green light, and so on. Okay, so if you just look at the source wavelengths in general, okay, so this is the whole electromagnetic spectrum. So if you just look around the radio waves, the wavelength is of the order of meters. But when we talk about the optical radiation, typically we are somewhere here. Okay, so this wavelength, if you just look here, it is somewhere from 400 to 700 nanometers. Okay, and this is a typical mercury vapor lamp wavelengths. Okay, so we have these different lines. So that different line or the different peaks will tell you what wavelengths actually we can extract. So with this one, we can actually get as small as about 365 nanometers. This is a typical eye line. Now, how this is related with the feature size. Now, again, I'll not get into those details. So typically, we can assume that if I'm using a certain wavelength of light, then I can expect in an ideal scenario, the resolution to be roughly half of the wavelength. Okay, so if I'm using a 400 nanometer of wavelength, I would not get better than 200 nanometer feature size. So this is again in ideal scenarios. Okay, then other losses will happen. So that will not even make it possible to get even 500 nanometers. So typically, if some of you already did the laser writing, okay, so in that case, the basic phenomena in case of a laser writing is the melting and evaporation. So in that case, again, the resolution is poor because you are heating up the material, then you are melting it, and then evaporating it. So even if you are using a, let's say, uh, if you just take example of the carbon dioxide gas laser, right? So wherein the wavelength is of a few microns. Okay, so in that case, the resolution would be a few tens of microns. Okay, so that much the scale differences. Okay, so in ideal scenario, if you are playing with the wavelength lambda, you wouldn't expect better than lambda by 2. Okay, so if I'm making use of a 365 nanometer, basically it's a blue light, right? As I go towards red light, the wavelength increases. Okay, so that gives us a clue. If I move from the red to the blue light, okay, so I'm reducing the wavelength. So if I use in that order, we can have the highest resolution possible. But still, we are talking in terms of 100 nanometers. All right, so already our expectation would be the features will be in the nanometric range. Then how to deal with this problem? So that's wherein the technology ventured into exotic sources. We need to go beyond the visible. So visible stops at blue light. So the smaller than the visible is ultraviolet. So that is well below 360 and so on. After ultraviolet, then we have next categories. Then you have this deep ultraviolet. So that will go up to the 100 nanometers. Then we have the extreme ultraviolet. So that will be few tens of nanometers. So okay, you can expect that when I use let's say deep ultraviolet or the extreme ultraviolets, already I'm talking in terms of some tens of nanometers. And still, if I want to go below with a single nanometer sort of a resolution, right, then what kind of a source we should look at? So this chart can give you the clue. The smallest wavelength, okay, so that actually goes into this X-rays or the gamma rays. Of course, the gamma rays we never use for the fabrication purpose, but yes, X-rays can be used for the fabrication purpose. And X-ray wavelength is few units of nanometers or up to angstrom level. But again, the X-ray using the X-ray source is not that easy as far as the fabrication is concerned. But yes, that is the possibility. Okay, so why that possibility is there? Because we are attacking the fundamental issue of the diffraction. And what we know as far as the diffraction is concerned, we can tackle with the reducing the wavelengths. And when the reducing the wavelength is concerned, we can reach up to the X-ray level where the wavelength is of few nanometer order. And that actually gives us sort of advantage. Yes, we can actually use these radiations with the smaller wavelengths in order to create a finer and the smaller structures. And of course, there are ultraviolet lasers available that can actually goes, for example, again, industry standard excimer laser. So this is again one type of a gas laser. So wherein we can get this wavelength. So that is about 156 nanometers. Now, what's the problem with reducing the wavelength? Okay, so is that easy to have this wavelengths? Again, the answer is no. Very first thing is that to have such short wavelength sources, typically from ultraviolet to the X-rays, again, is not easy. It turns out to be extremely costly in order to maintain this sort of a short wavelength sources. This is one thing. Second thing is coming from the instrumentation. Although we have these radiations, we require optical system in order to manipulate this bits. Okay, so from the source up to your vapors level. So how do we manipulate that? Because in case of our visible system, we have this glass that acts as a glass of the quartz, from which you can actually make the lenses so that you can project it. You can actually steer the beam and fabricate. But when you go to this smaller wavelength, it becomes quite difficult. Okay, it becomes quite difficult to have the materials that can be used as a lens. Okay, so the lens itself becomes extremely costly as far as this UV lasers are concerned. Okay, so compare this is what you use in case of ultraviolet lights and so on. And in fact, when you go up to the level of X-rays, you won't find any material that will refract, okay, and it will focus it down. Now, we're just talking about the electromagnetic radiation here. So, what could be the alternate ways with which actually we can actually play with this lambda? Then comes a very interesting phenomena. Okay, so when I talk about the electromagnetic radiation here, so ideally we're talking about photons, okay, or we're talking about wave nature of light, right? Now, if we just take a contrast and we'll try to see the particles, okay, especially particles accelerated at the higher speeds and so on, they show the other characteristic. Already we have a known duality as far as the light is concerned, whether light is a particle or whether light is a wave. Okay, certain phenomena they explain via wave nature of light, and for certain phenomena we require a particle nature of the light. In contrast, if you just look from the particle perspective, okay, so any physical particle, the particle can exist or it can actually show us very peculiar behavior as if it is a wave. So this was demonstrated. So just like we have a duality as far as light is concerned, photon is concerned, similarly we have a one more duality wherein a particle with a mass, it can also show a wave-like character. Okay, so this was demonstrated with the electrons. Now on the screen, what you see is bombardment by an electron through a slit. Now, if the light is traveling to the slits, open slit, you would expect if it is a sorry, not light, if it is a particle is traveling to the slit, you would expect, let's say if I have the two openings, and if we bombard these two openings, let's say this is a sort of a mask we have, and if I bombard these two slits with an electron or the series of electrons, you would expect they are the particles. Ultimately, only this much region it will pass through, and on the target screen, similar pattern will emerge. But instead, the pattern emerged is something like this. So this is quite explainable when we have such openings when we exposed it via light. Okay, so therein we say that the phenomena like diffraction and the interference, they will occur. The light will scatter or it will get diffract. Wave will get diffract through this opening, and we'll have this a fringe pattern over the screen. But here we're dealing with electrons and particles. We wouldn't have expected that sort of a phenomena happening. But with the electrons, this was demonstrated. So what does that mean? The electrons or the particles in general, okay, so they behave like a wave. Now, when we say the particle behave like a wave, that means it will have a wave-like characteristics. And what are the wave-like characteristics? The wave is known by its wavelength. So if the particle, sometimes we call it as a matter wave, if it exists, what are the associated wavelengths? So that can be calculated. I'm sorry, someone is scribbling.
I think yesterday also we faced the same kind of problem from Dr. Ashim Tiwari sir. Sometime the whiteboard line were coming, but I have disabled the participant.
Okay, fine. All right, I don't know whether this will go away or not. So let me just see if I can, if this is coming from this Zoom. Yeah, so this is not, okay, I think. All right, let's see if it remains, or is it way with which you can clear that?
We can see those yellow, in certain lines on the, slide itself.
Okay, so let me go to the next slide. Let's see if it.
Yeah, check with the next slide.
No, it's still there. Yeah, it's annoying. Blinks, not anything else.
Can you just disable the
Okay, anyway, I'll just continue.
Can you just disable and again, share your presentation so that it will go away? Yesterday also we faced some kind of problem when Dr. Tiwari was delivering his talk, so it went away after sharing.
Okay, okay.
Yeah,
Okay, I'll just try stop sharing and let us see.
Yeah, Dr. Mote sir, the voice breaking is also coming. Is there any problem from your speaker?
Yeah, sometimes there is some internet issues. Yeah, you just let me know. You can just type in. You can message me on my mobile if it is quite persistent. I can little bit break. Yeah.
Okay, sir. Okay. I will.
Okay, I'm just stopping the presentation.
Yeah.
Okay, I shared the slide. Can you see?
Yes, sir. It is visible now.
It's visible?
Yes, sir.
Okay, fine. Thanks.
It's not visible when I see on the screen. From host side, it is not there. Those kind of yellow lines. There is no line now. So you can go ahead, sir.
Yeah, but
continue. Yeah.
Okay, so I'll just carry on.
ഓർമ്മയൊക്കെ കുറഞ്ഞു അല്ലെങ്കിൽ പുള്ളി ഈ ഇതിനകത്തൊന്നും വെളിയല്ല. പുള്ളി വാങ്ങിക്കുന്ന, പുള്ളി അങ്ങനെ കാശൊക്കെ എല്ലാവരും വാങ്ങിക്കും, പക്ഷെ പുള്ളി അങ്ങനെ വാങ്ങിക്കുകയല്ല. പുള്ളി വാങ്ങിക്കുന്നത്, പുള്ളി ഇപ്പോ ഇലക്ഷൻ ആകുമ്പോ എനിക്ക് നേരത്തെ തൊട്ടറിയാം.
Please continue. Over to you, Dr. Mote, sir.
Okay, fine. That's it. So just may I request, I mean, if any of participant by mistake they have kept the mic on, please mute it. Okay, so from the photon now we are just ventured into particles. Okay, and I'll just let you know why we are talking about this. So basic premise is that particles like electron, okay, so they show some wave-like character. So this is quite visible here. So it's a nice fringe pattern emerged on the screen. Now the question is, if the electron is showing the wave-like character, what is the associated wavelength? Now it turned out to be, so just, I'm sorry. Okay. Okay, I just missed the form. All right, so so that particular wavelength, okay, so with which electron is moving or showing, behaving like a wave. Okay, so it will be decided based on how we accelerated it. Okay, so with what energy basically that electron moves, and that energy will decide on the associated wavelength. Okay, and simple physics will tell you the associated wavelength, we call it as a de Broglie wavelength. And with few hundred kilovolt acceleration imparted to these electrons, we can actually get a wavelength of a picometer. Okay, so that is much smaller than the nanometer. Now you can guess where we are heading to. Okay, so far what we talked about, wavelength is a solution to the diffraction problem. Now we have a particle that can be that is behaving like a wave, and the associated wavelengths are far smaller than the X-ray wavelength what we are seeing. So why not we make use of this particle and we take advantage of their wave-like character for our fabrication purpose? Because if we use this one, associated wavelengths are so small, then the diffraction will be at a almost negligible level, so that we can expect, or we can even think of creating the structure of a nanometric particle. And that's where we have this electron beam systems coming in. Okay, so this is a typical electron beam systems. So before getting into the fabrication using this electron beam, a parallel application that most of us are aware is in the microscopy. Okay, so I mean, you have a certain material, you try to see through the optical microscope, but if you want to get into the next level of resolution, right, then what we say, we go to the scanning electron microscope, or the SEMs. The reason is because we are dealing with the scanning electrons. Okay, the electron behaves like a wave, associated wavelength is so small, so diffraction problem is minimum, then you actually get a better resolution. Okay, so the problems what we face in the microscopy, they are fundamentally same as we face in case of a fabrication. Okay, so essentially, if you have seen so far when discussing the optical fabrication, we are talking about projecting the mask. Okay, so it's basically a microscopy exercise. Okay, so at the fundamental level, both are the same. So what you see through the SEMs, okay, in a similar way, now instead of just taking the image, what we are doing it, we are exposing this electron beam, over the material, and we are getting the patterns. Okay, so the basic SEM system is very similar to your microscope. Again, I'll not get into those details. So what we need in case of optical microscope, we'll be having a light source. So here we have this electron source. In case of optical microscope, we have the lenses. Since we are dealing with the electron beam here, we'll be having the electromagnetic lenses. So that will basically steer the beam. It will focus the beam, and it will be narrowed down to a point. Now, one major difference that I must emphasize over here when we talk about the optical lithography and E-beam lithography is, in case of optical lithography, we need a mask. It is a one-time exposure. So in a single exposure, we get a complete structure fabricated. Okay. But here in case of electron beams, typically, we don't have to use a mask because we already narrowly focused this beam. What we have to do, we have to trace a structure. So just like, if you take a crude analogy of a CNC milling. Okay, so again, in a CNC milling machine, you do a point by point machining. Okay, so just like you are doing a molding operation, you're preparing a CNC molds. Okay, so wherein you go with point to point machining. But once the mold is prepared, if let's say if you are preparing it for the injection molding, in a single shot, you are going to have the final component fabricated. All right, so when we fabricate with the E-beam, it's a point-to-point method. It is going to be time-consuming in that sense. But once, if you are using the optical lithography system, you have to prepare a mask. But once the mask is ready, your fabrication becomes quite fast. It is just like a flashing the light. Okay, so in that case, entire structure will be transferred in a single shot. Okay, so that's the difference between a serial writing, which is a point-to-point, to the parallel writing. And perhaps that is the reason we get a very high resolution with the E-beam system. But as far as the high throughput production is concerned, okay, so just like a chip making or the sensor fabrication and so on, we cannot use this E-beam lithography because it tends to be expensive as well as it tends to be very slow because it will always do in a point-to-point fashion. All right, so where the advantage of the E-beam system is, let's say if you want to fabricate a high resolution mask, okay, so that to be used, let's say in our optical lithography system, then we can have that one-time investment. Just like again from the macro world, if we want to have a mold to be prepared, we'll prepare it using, let's say, EDM machine or the CNC milling machine. It is a very time-consuming process, but that is a one-time investment. And once your mold is ready, then that can be used for the thousands of components. Let's say if it goes into the, let's say, injection molding machine, it can produce at a large scale. Okay, so you can take an analogy with your E-beam lithography system and the optical lithography system. And of course, there is additional advantage with the E-beam lithography is the resolution. Okay, so that is what we should not forget. Okay, so now how the E-beam lithography work? Again, it's very similar to optical lithography. We are not going to create a structure directly to the target material. In that sense, it's similar to the optical lithography. There also we said we are never going to make a structure directly over the substrate, but we're going to make a structure with some intermediate material which is responsive to the radiation. So in case of a photolithography or the optical lithography, it was a photoresist, essentially a polymer, which is sensitive to the light. Now, since we are using an electron beam, the material or the intermediate material, again, we'll call it as a resist. Okay, so that resist, we call it as a E-beam resist. Okay, so first exposure, again, here it will be on a point-to-point basis. If you just recall the example I gave at the beginning, let's say if you want to create a, let's say, pocket. So in that case, we had a mask. Over the mask, we had binary toning. with which actually we expose the resist. Now here we don't need a mask because we already have this electron beam, and that can be scanned across for a given structure. Okay, so just like now it is exposed with the electron beam, so this will be scanned over the desired region. Now this area is exposed, then we go with the development. So that will take out the portion over here, and then rest of the resist will act as a mask for the material beneath, and then we can play with this product. Okay, so now you can see it here. Either we can go with the deposition. The deposition is going to be selective in the sense. Let's say if you deposit now, what will happen? Uh, it will get deposited directly over here because that is opened up area, and rest of the material will get deposited over this top one. Then you lift off, you take away this resist. So what will happen here? You get a final structure. Okay, so this only if you look at from this step, we have a different. Rest of the processes are quite same. Okay, so in the sense of this pattern to deposit a structure. Okay, so just like now we started with this resist, we exposed with the beam, whatever the structure we want to create, that is developed. Okay, so that we have these recesses created. These are the openings in the resist. And then you have this deposition. So typically, what is shown over here is the gold deposition. There are many methods with which you can actually deposit a structure. The E-beam evaporation is one type. So you notice here the deposition is happening this way, and then with the lift off, you basically get rid of this resist. So what you left is, what you have is the pattern gold nanostructure. So you can see there are a variety of various patterns are. Okay. Other way is the material removal. Now what we have here, resist, you expose it with the plasma for the plasma etching. Now this resist basically protect your structure, and wherever the openings are, the plasma can actually reach up to the base and it will start removing the material over here. So you get a pattern created via material removal. So either you can go this way or material removal way. So that flexibility is again from the application perspective. Because you can see it here, various nano patterns are being generated via etching method. So deposition method and the etching method. Now this process can be used along with our optical lithography. Okay, so what you see here, so this is again a few of the structures we created for photonic applications. So the complexity of the structure is, again, these are micro lenses. Okay, so what you see here, so this gray region, okay, so this is gold. Okay, so the gold appears very different when you see through the SEM. Okay, so it appears like something else. Okay, but that is a gold. You need to believe me. Okay, and this gold is deposited over a glass, right? And now if you see here, there is a ring-like a structure. So we opened up this structure so that the dark here is the beneath glass. So that means we have this opening. This is ring is open. And in addition to that, we have one step created. So this is a step region. Okay, so this is a hierarchical structure in the sense. Okay, so wherein we need to make use of multiple processes. Okay, so what we did, we make use of two processes, two particles basically. One is electron beam based process and other is ion beam based process. So with the electron beams, basically what we tend to achieve is the selective deposition. Okay, so that step is seen over here.
Sir, namaskar म्हणलं, बोला.
Okay, so we created this opening with the E-beam lithography because this opening was quite small. We wanted to have a step-like structure. And then finally, we opened up this region with the ion beam system because ion beam system can directly remove the material. So all these dark rings, okay, so those dark rings were fabricated using the ion beam milling, and this deposition.
त्याच्यानंतर त्याला हातच लावलेला नाही सर, to be frank. बरोबर आहे, बरोबर. मग आता काय करायचं बघा त्याच्यावरती पुढे. हा हा बरं. बरोबर. बरोबर. कारण सर मी या आठवड्यामध्ये माझा अटलचा एफडीपी चालू आहे. हा एवढा झाला कीच मग त्याच्या पाठीमागे लागतो. आता परत मी सेशन बंद करून फोन घेतला.
Sir, your mic is on.
पण घेतो अपडेट घेतो. एकदा आधी दिवस स्प्लिट करून घेतो अपडेट. नाही आहे सर, तुम्ही म्हणते ते बरोबर आहे.
Dr. Shinde, I think your mic is, please mute your mic so that I can just carry on.
Priority त्यांचे दररोज बदलतात. बरोबर. बरोबर. मी बोलतो सर, बोलतो आणि मग तुझी अपडेट करतो. ओके सर, ओके ओके.
डॉक्टर शिंदे.
या.
तुमचा माइक म्यूट नव्हता, सो जस्ट आय स्टॉप इन बिटवीन. Okay, so now I'll just move on. So this is the beauty of the process. I mean, if you have some challenging structures, not just for your industry production or the high throughput, but if you want to test certain phenomena, these tools becomes quite useful. Okay, so so this is the de Broglie wavelength, what I was talking about at the beginning. Of course, let us not worry about the complicated relation over here. So what we need to understand is the acceleration voltage with which we are going to drive the electrons, right? So for example, if we just accelerate the electrons are with the 100 keV, the corresponding wavelength is already fraction of nanometers. Okay? So that's the reason we expect a better resolution with any other optical lithography methods. All right, so I'll just give you the overview of various sources that are being used. So just like the very popular source with the C-beam system is the thermionic, which is the low cost one. But in order to have the most stable source, we go with the field emission, the way with which actually we extract electrons. We extract the electrons from the filament. And then these electrons will be sent into E-beam column and you get the focusing down. Okay, so I'll just give this region. Now I'll get into how the electron actually reacts with the material. So there are many possibilities as the electron penetrates into the material. Okay, so this falls into the microscopic domain, but I just give you the glimpse of it. Okay, so apart from other reactions, because electron is carrying a mass, it is hitting with the high velocities. So as it interacts with the matter, okay, so either it will just simply pass through or it will hit the material, it will hit the atoms and it will cause some atomic level changes. Okay, so in that case, if you just take a simple phenomena, so what is possibility? Electron actually can penetrate into the atom. It can knock out electron from the inner orbit. If such electron is removed from the inner orbit, in order to now the vacancy is created. Okay, so this is not a stable phase. Okay, so in order to occupy this vacant position, so there is one possibility: the electron from the higher orbits, they will jump into the lower orbits where the vacancy is created. So while doing so, from the higher to lower energy, this electron should lose the energy, and this energy, whatever it is losing, it will be emitted in the form of a photon. So we call it as a photo emission. There is one more interesting phenomena is possible, wherein now what we are seeing here, when the electron jumps to the inner orbit, it emits a photon. Now this photon in turn can dislodge electron from the outermost orbit. Okay, so first electron is knocked out, vacancies energy levels, one more electron is getting transferred, it loses energy, and whatever the energy lost is taken by the outermost shell, and one more electron is released. Okay, so either you get a photo emission or you get an electron emission. This electron emission we call it as organ. Now, all these phenomena, they are characteristic of the material what we are dealing with. So if we capture these emissions, it will tell us more about the material. Case of a resist, and in fact, if we use electrons, just like you use in case of SEM, it can tell us about topography, and more than that, it can tell us about the kind of materials you are investigating. And there is one more interesting phenomena that happens with electrons, which is quite important as far as fabrication is concerned. If you just imagine, if you are dealing with a very heavy material, I mean heavy in the sense high atomic mass material. So what happens? With the high atomic mass materials, you have a large number of protons at the nucleus. So electron actually can penetrate. Okay, so one possibility, what we said, it knocks out the electrons from the target material. The other possibility is it will simply enter into the atom, but due to the heavy nucleus, these electrons get deflected. Likewise, it undergoes many interactions through various atoms, and almost it is getting U-turn through the materials. So it enters the material and actually it gets out of the material without actually knocking out any electrons from the target material. So one possibility, what we said, either it is knocking out the electrons, and these electrons we call it as the secondary electrons, or the auger electron we have seen in previous case, or our incident electron can simply just travel through the material, almost get back to the original direction. So we call this as a backscattered electron. Okay, so backscattered electron, again, when it is possible to have it, when we have this heavy nuclei. So this property is quite useful when we do the imaging exercise. For example, as you notice here, the first image, wherein the two materials so this is the nickel material. Okay, so over the nickel we have this titanium wire. Okay, if you just see here the first image, how we obtain this image with the capturing the secondary electron, that means the electrons which are knocked out. And if we capture the backscattered electron, if we capture this backscattered electrons, this is the other image. Now what we have seen in case of a backscattered electrons, they are a function of atomic masses, because heavier the material, more will be the backscattered electrons. So here we don't get a good contrast, but in case of backscattered electrons, we can see a good contrast. As we see, this image is bright, this image is dark, that is coming from the material. Why it is happening? Because this is the nickel. Nickel is heavier than titanium. So more backscattered electrons are emerging from the nickel. That's why this region is bright. Less number of backscattered electrons from this titanium wire. So this appears to be dark. So that's the reason you get a better contrast. So when you do the imaging exercise, basically you try to take advantage of the material properties and you can obtain a better images. Okay, so I'll just skip this portion. These are various scattering events. Okay, so if you look around how the actually electron travels into the material. Okay, so once it gets inside the material, it doesn't travel in a straight path because it undergoes multiple collisions. Some collisions are elastic, some collisions are inelastic. So it takes, so although we have a very narrow electron beam, but when it goes into the material, it actually gets broader. So what you see, this blackish region is the trace of an electron. So you can see if I increase the energies, it penetrates more, but at the same time, it also scatters more. That means I get a broader exposure. So when we go for the fabrication, we would expect this much region of your resist will get exposed with the higher energies. But with the lower energies, the scattering will be less and your exposure will be smaller. So the smaller feature can be obtained. Okay, so there are various ways with which actually the exposure can occur. So very basic system, as we said, we go point by point. Let's see if I want to trace this domain, I need to discretize it into points, and at the individual pixels, we actually traverse the beam. So typically, in order to capture this area, we require almost 100 shots. Shots means for every pixel, we are opening up the electron gun. Okay, so we need to bring the gun at individual pixel and shot it so that at least 100 shots are required. But in order to improve the process, now the exposure, instead of having exposure in terms of pixels, the exposure can be with certain areas. Okay, so in that case, we need to modify beam column so that such area exposure is possible. So we need to bring in additional apertures. Okay, so with which the same area now can be exposed rather than point, but as a segments. Okay, so in that case, we reduce from 96 shots to the 6 shots. So this will happen if we have the fixed area. Now, if you have the flexible area, okay, so in that case, within 3 shots, actually we can capture the area. So these are the other advances with which throughput of E-beam lithography basically can be improved. But again, these are not that commercially popular yet. Okay, so most of the systems what are being used, they are this point-to-point scanning systems. Okay, so I'll just give this version. Okay, so I talk about the backscattered electrons. Okay, so there we took advantage of the backscattered electrons from the imaging perspective. But sometimes this backscattering effect can cause a problem in lithography process. Now just imagine, now we have this resist over the substrate. We are just tracing these lines because these are the pattern we want to fabricate. And with the electron beam, we basically scan it across. Now what we know, the resist is a low molecular weight material, but substrate, just like a silicon, which is quite heavier than the resist. So what we know, the electron can penetrate into the resist as well as it can penetrate into the substrate. So the property modification will only happen at the resist level. The electrons that are entering into the substrate, they are not going to cause any property modification in the substrate. But instead, what will happen? There is a possibility that many of the electrons, they will undergo the backscattering process. Backscattering in the sense, they will almost return to the opposite direction. Okay, so parallel to our. So these are the possible backscattering events. So when they come back, so these events, they should not cause any problem because they are getting into this exposed region. But the problem arises if it actually goes into these domains. Because as if we are exposing this region, right? We do not want to expose it. That's the reason we are scanning the electron across. But these backscattered electrons, they can actually reach this unexposed region, right? And in that case, instead of getting a perfect patterns here, we get patterns like this because this is unintended, unwanted exposure that is getting. Okay, so this exposure should not cause any harm. This exposure should not cause any harm, but the exposure over here, they will actually create a trouble in our structure. So when we do this E-beam lithography, we need to take into account, especially when we are dealing with a dense structure, as I pointed out earlier. So this phenomena actually we need to worry about. Okay, so just like you see it here, especially the corner regions. So what you see, the dark region here is because of your backscattering electron. So this effect, we call it as a proximity effect. So this is unintended exposures, especially happening at the corners, because when I scan beam over here, when I scan beam over here, so backscatter electron eventually will reach at this corner outside the region of interest. So we need to account for that. We can estimate that. So we can actually make corrections into our exposure. Just like if I avoid exposure, giving exposures over here. the backscatter electron actually can give us a correct exposure. Okay, so there are again some complex algorithms, especially for the periodic structures. Okay, so wherein we try to balance this back exposures. So we can have a base exposure and over which superimposes the background exposure, so that ultimately all the exposure is at the same level and we get a nice uniform exposure, so that we get a dense pattern. All right, so quickly I'll just wind up with the final thing. I'll not get into this all of the effects. Now the final thing is that so far we have seen two-dimensional structures. Okay, so that can be easily made. But what if I want to make a three-dimensional structure? Three-dimensional structure in the sense, along the thickness, the feature dimension, they vary. So in that sense, the idea is, for example, if I want to create, let's say, a pyramid. Okay, so the pyramid is having a varied thickness, varied lateral dimensions along the thickness. So in that case, a single exposure will not ensure that you are going to have three-dimensional variations or the variation along the thickness. So in that case, what we have to do, we have to basically give the different doses. We need to discretize this entire structure. So in this case, if this is the pyramid we want to have, so we want to have the maximum thickness at this level. Okay, so in that case, we can have the different dose at this level and extreme dose at the edge level. So this will ensure the differential exposure. So the solubility will be different at the edges, and as we move towards the center, because of the varied dose, again the solubility will be different, right? So when we actually develop this resist, the different quantum of resist, it will get dissolved, and what finally you get a three-dimensional structure. And of course, this staircase effect can be minimized if we have a very small segment with a different doses. Okay, so that's how we can see it here. So again, this is a very crude definition. We have only 5 lines here, so you can see it here. The steps are being created because different doses are given along these lines. But if you just reduce this length, widths, so you can have the smooth structure here. All right, so you can see it here, various imprint steps being fabricated. You could see this wedge-like pattern being created, and this pattern will give us imprint stamp, and once we have this imprint stamp, that can be used for the mass production. Okay, so with this I'll stop here because we need to have some time for the discussion. So once again, I thank you for your patience, and I hope I touched upon some basic aspects of lithography and the need for additional means of fabrication. So I'll just open it now for the question and answers. Thank you.
So the participants are encouraged to ask the question by unmuting yourself, or you can put your question in the chat box. So Dr. Mote will answer those questions. Over to you, participant.
Sir, is it possible to use a plain polarized light for masking process and optical lithography?
Okay, so when you say the plane polarized, do you mean by the, are you talking about light? What exactly you mean by the plane polarized? Are you talking about the broadband light or something else in your mind?
So you talked about the mercury lamp, right? So from the mercury light, if you are taking the light and then we are plane polarize it, and then after that has been used for masking purpose, it is whether it is possible to get this kind of a thing.
Well, I mean, mercury lamp is quite popular earlier because that was the available source. Okay. Now we can again use the mercury lamp with the filters, wherein we can actually make use of a single wavelength. Okay, so mercury lamp actually gives us quite peaks at certain wavelengths. Okay, so we call those as the lines. So they can be easily filtered out and can be used for the lithography purpose. Now, as far as the polarization is concerned, because polarization is different concept, because it has nothing to do with the wavelength. Okay, so what we are mostly interested in is the wavelength. Okay, so which wavelength we use, and that will define the resolution. Now, as far as the optical lithography is concerned, polarization of a light. Okay, so that doesn't have much bearing on your structures. Okay, so wherein in the polarization, what we basically look at the plane of vibration, okay, of photons. Okay, if it is unpolarized light, we know it is vibrating in all possible directions. But when we talk about the plane polarization, right, it is happening in a particular orientation and so on. So as far as the resolution is concerned, the polarization doesn't have much influence on the resolution. I mean, it doesn't have much influence over the feature size what we're talking about.
Okay, okay, sir. Thank you.
Any other question, participant? Please come forward and go ahead with the asking few of those questions and doubts, because this is the right platform where you get the expert to interact with them rather than writing the emails and asking those queries. So I appeal all the participant to ask the question if you have any.
So in fact, I'm just typing in my email address. Of course, you might have shared my
Yeah.
contact details and all. Okay, so if they want to have any additional information, any other question, any other discussion, some other details, okay, so they can always write to me.
Yeah, participants are appealed to note down the email ID of Dr. Mote sir. In case if you have any doubt, you can write an email and he will be happy to answer your all the queries. So if there is no question from the participant to ask at this moment, so now I will be winding up with a few notes from my side. So first of all, I would like to thanks Dr. Mote sir for taking his valuable time and spending with us at this evening. He was busy with the other activities and responsibility at institute, but he accepted our invitation and delivered the talk on the e-beam lithography. He's the man in micro manufacturing and fabrications. If you look over to the slides starting from the very early stage to the what is the state of art of this micro manufacturing, so it is a very I can say the work what he has created so far is a state of art facility in the mechanical department under the nano micro manufacturing division. So he and his student and his group are doing a huge work on the fabrication of such kind of micro and nano structures, which are widely being right now being used in the various application in the industry as well as the devices and systems. So I appreciate the way Dr. Mote sir, he has shared the work. Though there are certain projects which are from the DST and some of those are from the consultancy and so, but he tried to give the best of best state of the art, what they have developed, and the ongoing project through the basic concept of lithography and making the smaller and smaller thing from top down approach to make the things in the nano and micro level. So with these few words, sir, I thank you again once again on the behalf of Department of Production Engineering, VJTI Mumbai, and Atal FDP, AICT Atal Learning Academy for spending your time and delivering this expert talk on the E-beam lithography on the day 2. So once again, thank you, and in future we will be looking ahead for such kind of engagement with us. Thank you, sir. Please share your few of
Thank
those
you.
documents what I wrote in the email, and accordingly we will proceed for the
Okay.
post FDP work. Thank you, sir.
Okay,
And
fine.
share your PPT in the PDF form, whichever is shareable, and then we can share to the participant in post of this
Okay.
session.
All right. Yeah.
Okay, sir. Okay, thank you. Thank you, sir.
Thank you.
So there are certain announcements from my side. Participant, tomorrow morning, day 3, we will be having the session on time. 8:30 we will start again. So you have to join 5 minutes before. Do not join late. And you can send your feedback and attendance responses through the Google Forms, shared with you, and that will be collected at our end. And definitely we will be sharing the link of the videos very soon. Few of those PPT, whatever we will receive from those speakers, will be shared to the all email ID through the drives, and you guys can access it through the drive. So with this note, I conclude today's all 3 sessions are over, and we will meet tomorrow at 8:25 early in the morning. If you have any concern and queries, kindly you can share with me. I will wait another 2 to 3 minutes for taking your queries and concern if you have any.